There's a silence between the stars, a gulf so wide that even light, the universe's fastest traveler, takes years to cross it. Alpha Centauri, our nearest stellar neighbor, glimmers just 4 light-years away. In cosmic terms, it's next door. In human terms, it's forever. If you left tonight aboard our fastest ship, you wouldn't arrive for tens of thousands of generations. Yet within that unreachable distance lies a profound truth about who we are and what it means to dream beyond our limits. Like and subscribe before we drift further. It helps this journey continue through the dark. Tonight, we'll follow the light across the impossible. Let's begin. Just beyond the reach of our telescopes lies Alpha Centauri, a system of 3 suns dancing in gravitational embrace. At only 4.37 light-years away, it's close enough for our instruments to see, yet far enough that our species may never touch it. When you look up on a clear night in the southern hemisphere, you might catch its faint shimmer, a golden point of light that flickers just above the horizon. To the naked eye, it seems ordinary, a star among countless others. Alpha Centauri b. Smaller, warmer, more orange in hue. And orbiting farthest away, the faint red ember of Proxima Centauri, the nearest of them all, glowing softly in the void. Together, they form a celestial waltz, bound by gravity, weaving around one another in a slow dance that has lasted billions of years. For centuries, we've looked toward them with longing. When the first telescopes revealed that some of those distant lights were actually other suns, the human imagination ignited. If our sun could host life, then surely theirs could too. The Alpha Centauri system became the first step in a dream, a bridge from our solar shore to the next archipelago of stars. 4 light-years. Just 4. The number felt almost comforting, almost attainable. After all, light crosses that distance in only 4 years. A blink on cosmic scales. But the universe hides its difficulty behind simplicity. 4 light-years is a chasm so immense that every spacecraft we've ever built, every engine we've ever imagined, collapses under its weight. The Voyager probes, traveling faster than any human-made object in history, would need over 75,000 years to reach Alpha Centauri. 75 millennia, longer than modern humans have existed as a species. If we launched them today, they would arrive in a time when our languages had changed beyond recognition, when our species might be something else entirely. And yet, that distance calls to us. The mind cannot help but lean toward it. It may have oceans, it may even have air. A world so close that we can already measure the faint dimming of its star as it passes before it. But between our world and that one lies a sea of darkness so vast that not even hope travels quickly through it. It is a strange contradiction. Alpha Centauri feels near enough to touch, yet impossibly far to reach. We can calculate its distance with precision, photograph its light, and chart its movements. But those photons reaching our eyes tonight began their journey in 2021. Every glimpse of that star is a message from the past, a postcard from another sun, written in light, delayed by 4 years of silence. Perhaps that is the truest measure of distance in the cosmos, not how far something is, but how long its voice takes to reach us. The space between our star and Alpha Centauri is more than just emptiness. It is the interval between what we can imagine and what we can do. And in that space, humanity stands, staring across infinity that looks deceptively close, waiting for the day when light itself will no longer be the only traveler between our worlds. Light moves at 300,000 kilometers per second, fast enough to circle Earth 7 times in a heartbeat. But even at that velocity, it takes more than 4 years for a single beam to bridge the gap between our world and theirs. It is the fastest thing that has ever existed, the universe's one true constant. Every sunrise, every reflection, every glimmer on the surface of the ocean is a whisper of this ancient traveler, photons born in the heart of stars, racing through the vacuum, carrying with them the story of everything they touch. Yet for all its speed, light also reveals the cruelest truth of space, that the universe is vast beyond all proportion, and that even the swiftest messenger is bound by its laws. When we say the speed of light, we often imagine it as unlimited, as if it were the key that could unlock the cosmos itself. But nature draws a hard boundary there. No information, no ship, no dream can outrun it. It is the ultimate speed limit, written into the very fabric of space-time. As an object accelerates, it gains mass. Push harder, and it resists more. Push infinitely, and you would need infinite energy to make it reach light's velocity. The faster something moves, the more it drags time and energy along with it, until movement itself becomes impossible. So light is not just fast, it is sacred. It is the measure by which the universe defines the possible. Astronomers call it C, a single letter that shapes all of relativity. It is the heartbeat of the cosmos, the ruler by which every distance, every moment is measured. Even time bows to it. At light speed, clocks stop ticking, lengths contract, and mass becomes infinite. Space and time blend into something strange, something we can describe with mathematics, but never truly feel. Every image of the universe we've ever taken, every galaxy, nebula, or planet, is light from the past. The sun you see in the morning sky is 8 minutes old. The nearest galaxy, Andromeda, sends us light that began its journey 2.5 million years ago, when early humans were still learning to spark fire. Even our own reflection in a mirror is a fraction of a nanosecond old, an echo delayed by the time it takes light to travel the width of your face. This is the strange paradox of light. It moves faster than anything in existence, yet it always arrives late. Every observation we make of the cosmos is really a glimpse backward through time. When we look at Alpha Centauri, we are seeing it not as it is, but as it was 4 years ago. A flash frozen in time, preserved in motion. And so, when we talk about traveling to other stars, we are speaking of chasing ghosts, of pursuing light that has long since moved on. To reach another sun, we would need to match the messenger that has already arrived and gone. But in a universe governed by the speed of light, catching up to your own reflection is as impossible as stopping time itself. Light is our window and our wall. It is the fastest path through the cosmos and the barrier that keeps us confined within it. Every photon reminds us of both our progress and our prison, a shimmering boundary between what we can see and what we can never touch. If we launched Voyager 1 toward Alpha Centauri, it would take over 75,000 years to arrive. Civilizations would rise and fall before its faint signal ever reached those distant suns. Voyager 1 is humanity's most successful castaway. Launched in 1977, it has crossed the boundary of the solar system and now drifts in the interstellar dark 24 billion kilometers from home. Yet even now, beyond the reach of our sun's magnetic breath, it has traveled less than a fraction of 1% of the way to the nearest star. The distance between the stars is so immense that Voyager's entire 48-year odyssey amounts to little more than a single step from the shore. If it could somehow continue on the same path, untouched and undisturbed, it would finally reach Alpha Centauri long after Earth's continents had shifted, after mountain ranges had risen and worn away again. By the time it arrived, our languages, our nations, and even our descendants might be unrecognizable. The spacecraft's golden record, its message of sounds and greetings from Earth, would be a relic from an ancient civilization that no longer exists. 75,000 years. It's a number that barely fits inside human imagination. Humanity lived in small bands of hunters and gatherers, with fire as our most powerful invention. If one of those early humans had watched Voyager launch, they would have seen it vanish into the stars before their great-grandchildren's great-grandchildren even learned to farm. That is the scale of interstellar distance. It's not measured in kilometers or miles, but in the lifespans of species. Our fastest rockets move tens of kilometers per second. To cross the gap to Alpha Centauri, we would need to multiply that speed by thousands. Even then, The journey would take entire civilizations chained together in time, each generation born knowing they will die aboard the same ship, never seeing the destination they were promised. Such a voyage would not just be slow, it would redefine what it means to travel at all. And yet, the slowness of Voyager's journey holds a kind of quiet beauty. In that endless drift through space, it carries a record of who we were, the music of Bach, the heartbeat of a mother, the laughter of a child. Across the centuries, long after the memory of its makers fades, Voyager will continue on, indifferent to extinction, bearing evidence that for a brief moment in cosmic history, we looked up and tried to speak to the stars. Perhaps one day, somewhere near another sun, another civilization will find that golden disk and play its messages. They'll hear the sounds of our oceans, the songs of our whales, and the voices of long-dead humans whispering greetings across the gulf of time. Voyager will still be moving, infinitely patient, endlessly slow, a messenger whose destination is eternity itself. In that silence between worlds, its signal continues to fade, weaker with every passing year, but even so, it persists. A single heartbeat in the dark, proof that speed isn't the only measure of greatness, that sometimes the slowest journey in history is the one that keeps our name alive among the stars. Space isn't just empty, it's mercilessly vast. Every extra kilometer doubles the cost, triples the risk, and stretches time until centuries become a single step. From the edge of our atmosphere, the universe looks serene, a silent, infinite canvas of stars. But for those who dream of crossing it, space reveals its true nature, not a tranquil sea, but an abyss of impossible proportions. Distance in the cosmos doesn't scale the way our minds expect. On Earth, traveling far means hours. In space, it means epochs. Between our planet and the nearest star lies a gulf so immense that even light, the fastest traveler in existence, takes 4 years to bridge it. And for anything slower, for anything human, it might as well be forever. We often imagine the universe as navigable, like a map waiting to be charted. But every mission beyond Earth is a war against distance itself. The more we push outward, the more the cosmos pushes back. To reach Mars takes months. To reach Jupiter, years. To reach Alpha Centauri, even at speeds unimaginable by today's standards, would take the length of recorded human history. Every kilometer is a demand for more energy, more patience, and more faith. This is the tyranny of distance, a law not of physics, but of scale. It governs every dream we've ever had of escaping our cosmic island. The fuel needed to reach another star increases exponentially with speed. To go twice as fast, you need 4 times the energy. To go 10 times faster, you need 100 times more. Every attempt to outrun the void becomes a negotiation between ambition and exhaustion. The farther we aim, the smaller we feel. Distance also multiplies risk. Spacecraft degrade, instruments fail, and cosmic radiation corrodes everything it touches. Even our most advanced materials cannot survive unscathed for tens of thousands of years. A journey to another star isn't just a voyage through distance, it's a test against time itself. Engines would need to burn longer than any civilization has endured. Guidance systems would have to operate flawlessly across millennia, untouched by repair. The sheer logistics defy comprehension. And yet, humans persist in dreaming of it. Perhaps it's because distance has always been our greatest teacher. Every frontier we've crossed, from oceans to planets, has expanded not just our reach, but our understanding of ourselves. The stars, unreachable as they are, remind us that striving is its own kind of arrival. The tyranny of distance may define our limits, but it also defines our courage. In a way, this vastness is merciful too. If the stars were closer, the sky would not be dark, and we might never have learned to wonder. The spaces between worlds create the silence in which imagination can echo. It's in that silence that humanity finds purpose, not in conquering distance, but in being humbled by it. For now, we remain tethered to our small blue world, sending signals that fade into the infinite night. Each transmission, each probe, each photon of curiosity we release into the void is an act of quiet rebellion against the tyranny of distance, a declaration that even if the stars remain beyond our grasp, we will always reach for them. The technology that took us to the moon is useless beyond our solar system. Chemical rockets burn bright, but their efficiency is pitiful against the scale of interstellar travel. They are the fiery engines of our greatest triumphs, the roaring columns that lifted Apollo into the heavens, the thunder that carried Voyager past the outer planets. For more than half a century, chemical propulsion has been humanity's only bridge to the stars. Every launch, every satellite, every space probe has depended on the same simple principle. Ignite fuel, expel exhaust, and let the reaction push you forward. It's beautiful, primal, and astonishingly powerful. Within limits. But in the vast emptiness between the stars, that brilliance fades into futility. A chemical rocket works by converting stored energy and propellant into thrust. The problem is that chemical bonds, even in the most energetic mixtures we can create, hold very little energy compared to what interstellar travel demands. The best engines today, those fueled by liquid hydrogen and oxygen, can propel a craft to about 17 kilometers per second. To escape the solar system entirely, you need roughly twice that. To reach even a tiny fraction of the speed of light, you'd need to multiply it by 10,000. Every rocket equation tells the same sad story. To go faster, you need more fuel, but the more fuel you add, the heavier the rocket becomes, which means you need even more fuel to lift the extra weight. It's an endless loop, a cruel paradox of propulsion. For interstellar missions, this becomes absurd. To accelerate a small spacecraft to just 1% of light speed using chemical fuel, you'd need more propellant than there are atoms in the observable universe. Our moon landings, extraordinary as they were, barely escaped Earth's gravity well. The Apollo missions traveled a mere 384,000 kilometers, a distance that light covers in little more than a single second. By contrast, Alpha Centauri sits 40 trillion kilometers away. Chemical propulsion is a spark trying to illuminate eternity. Even so, humanity keeps building rockets. They are symbols of our will to rise, our refusal to stay grounded. The sight of a rocket ascending through clouds, trailing flame and thunder, is more than engineering. It's poetry in motion. A reminder that we were never meant to stay still. But as magnificent as they are, chemical rockets are tools for local journeys only. They can carry us to Mars, perhaps to the icy moons beyond Jupiter, but never to another star. If you stood on the surface of a world orbiting Alpha Centauri and watched Earth through a telescope, you would see our rockets as tiny sparks, barely leaving the cradle of our system. They blaze brightly for moments, then vanish into darkness, their light swallowed by scale. Chemical propulsion was humanity's first step into the cosmic ocean, but it's also our anchor. The same fire that carried us skyward now binds us near home, unable to burn long enough to reach the next shore. To go farther, we must learn a new language of motion, one not written in flame and smoke, but in light, fusion, or fields, yet undiscovered. For now, the rockets sleep on their launch pads, silent monuments to both our brilliance and our boundaries. Their fuel is not enough, their fire too brief, but their legacy endures, whispering to the future, find a better way. To reach another star, we must first break free from our own. Escaping the sun's gravity well requires unimaginable energy. Most spacecraft barely escape Earth. We tend to think of space as freedom, an endless void beyond the pull of any world. But even here, in the cold silence between planets, we are still tethered, bound by the invisible hands of gravity. The sun holds every planet, every asteroid, every fragment of dust in its vast gravitational embrace. It is a cosmic jailer whose reach extends for billions of kilometers in every direction. To leave its dominion entirely, to step beyond the frontier where its pull fades to nothing, demands not courage, but energy. Unimaginable, relentless energy. Every spacecraft we've ever launched begins in layers of escape. First, it must break free from Earth's gravity, clawing its way upward against the planet's pull. That alone consumes the majority of a rocket's fuel, just to reach orbit, a fragile perch a few hundred kilometers above the surface. But escaping Earth isn't the end. Our planet itself is falling endlessly around the Sun, locked in a gravitational orbit that moves at 30 kilometers per second. To truly leave the solar system, a spacecraft must counter that momentum and climb out of the Sun's well. For comparison, a rocket needs about 11 kilometers per second of speed to leave Earth. To escape the Sun entirely from Earth's orbit, it must reach at least 42 kilometers per second, nearly 4 times faster. The Voyager probes, our most distant emissaries, achieved this by slingshotting around the giant planets, borrowing momentum from their orbits. Even then, they are not fast enough to reach another star within any human timescale. They are free, yes, but only just. Imagine the Sun's gravity as a deep, invisible ocean. Earth orbits near the surface, caught in a gentle current. The farther out you go, the weaker the pull becomes, but it never truly vanishes. Every kilometer farther from the Sun means climbing uphill against this unseen tide. And at the heart of it all, the Sun burns on, its mass a cosmic anchor that binds the entire solar system to its will. For humanity, this presents a cruel paradox. The energy required to reach another star must first be spent just to leave our own. The Sun, the very source of our life, is also the gatekeeper of our prison. Even the most powerful engines we can conceive, nuclear, fusion, or antimatter, must first pay this toll before they can accelerate freely into the interstellar dark. If you could watch from afar, you'd see our spacecraft as tiny sparks rising from a well of light, struggling upward through invisible resistance. The deeper you are in the Sun's gravity, the more it costs to climb out. And Earth, our home, sits deep inside that well, comfortably warm, but trapped all the same. Escaping the Sun's grasp isn't just a matter of physics, it's a symbol of every limitation we face. The Sun nurtures us, but it also binds us. It gives us warmth, yet it demands tribute for every attempt to leave. Perhaps one day, we'll find a way to slip its hold, a drive powerful enough to conquer its pull. Until then, we remain in orbit, forever circling the fire that both gives and denies us the stars. Launched in 1977, Voyager 1 has traveled more than 15 billion miles. It is the farthest human creation from Earth, and it has yet to leave the neighborhood of the Sun. Out there, beyond the planets and the reach of solar wind, Voyager 1 drifts through the interstellar dark, a single, silent messenger from a civilization it can no longer hear. Its tiny plutonium heart still glows faintly, powering instruments built half a century ago. Each signal it sends takes more than 22 hours to reach Earth, whispering across the void at the speed of light. By the time its message arrives, the data it carries is already a memory. Voyager 1 was never meant to live this long. It began its journey as an explorer of the outer planets, a brief mission to study Jupiter and Saturn. But when its cameras captured the first close-up portraits of those worlds, humanity couldn't bear to stop. It was redirected again and again, sent farther, past the orbits of Uranus and Neptune, until finally, there was nothing left to visit. Its instruments were turned outward, toward the stars, and it continued on into the unknown. In 1990, before shutting down its cameras forever, Voyager turned to look back one last time. From 6 billion kilometers away, it captured the famous image known as the pale blue dot. Against a sunbeam scattered by the camera lens, Earth appears as a speck smaller than a pixel, so tiny it could be mistaken for dust. Every human life, every empire, every joy and sorrow that ever existed, all compressed into that single dot. Carl Sagan, who helped inspire the photograph, called it a mote of dust suspended in a sunbeam. Today, Voyager 1 has crossed into interstellar space, beyond the influence of the solar wind. But it hasn't escaped the sun entirely. Even here, the star's gravity still holds it, faintly, like a distant memory. It will continue to orbit the galaxy with us, bound by the same invisible thread, for billions of years. The sun's reach extends farther than its light. Its golden record, bolted to the side of the spacecraft, carries greetings in 55 languages, the sound of waves, laughter, thunder, and music. Etched onto its surface is a map showing the position of our solar system among nearby pulsars. An invitation, or perhaps a warning, to anyone who might find it. In the vast silence between stars, it drifts on, the last surviving ambassador of a species that once looked up and wondered. One day, its power will fade completely. Its signal will weaken until even our most sensitive antennas can no longer hear it. There will be no announcement, no sudden silence, just a slow fading into the cosmic background. A whisper swallowed by eternity. And yet, that whisper will keep traveling, long after our world is gone. It will move between the stars, untouched by time, carrying with it proof that we once existed, that for a fleeting moment we built something that escaped the cradle of the sun. Voyager's last message isn't a signal. It's a legacy, that curiosity endures longer than empires, and that even the smallest voice can echo forever in the dark. Einstein's relativity dictates that nothing with mass can reach the speed of light. The faster we go, the heavier we become, until acceleration itself becomes infinite. This is one of the universe's most unbreakable commandments, a boundary etched not in stone, but in space-time itself. No loophole, no clever engineering trick, no secret technology can change it. The cosmos allows light to move at the ultimate velocity, but anything that carries even the smallest amount of mass is chained forever beneath that limit. The closer we push toward it, the harder the universe resists. At low speeds, motion feels obedient and predictable. A car accelerates, a plane takes off, a rocket burns and moves faster. But once you begin to approach a significant fraction of light speed, reality itself starts to warp. Time stretches, distances contract, and momentum grows like a tidal wave that never breaks. The equations of relativity describe it perfectly. As an object's velocity increases, so does its relativistic mass, the amount of energy it takes to keep accelerating. To reach 99%, the speed of light would require hundreds of times more energy than to reach 90%. To reach 100% would require infinity. It's not that the universe doesn't want us to go faster, it's that the structure of reality forbids it. The speed of light isn't just a number, it's the architecture of existence. Space and time are intertwined, and light defines the way they interact. When something moves, it bends time around itself. At light speed, time would stop completely. From a photon's point of view, there is no before or after, no distance traveled, just instantaneous existence, from emission to absorption. For light, the entire universe is a single moment. For us, trapped in time. This law has profound consequences for our dreams of reaching other stars. No matter how powerful our engines, no matter how efficient our designs, we can never truly catch light. We can approach it asymptotically, but never touch it. The energy cost would be unimaginable, an exponential climb that turns technology into futility. Even a small spacecraft, traveling at half the speed of light, would require more energy than all humanity produces in an entire year. At those speeds, space itself becomes a wall of resistance. Some scientists speculate that perhaps one day we could find ways around this limit, not by accelerating through space, but by bending it. Concepts like warp drives or wormholes attempt to sidestep the rule, moving space itself instead of moving through it. But even these theories require exotic forms of energy, negative mass, quantum fields, or space-time distortions that may not even be possible. For now, they remain mathematics painted with imagination. In the end, Einstein's speed limit is less a punishment than a kind of cosmic mercy. If light speed were easy to reach, the universe would be chaos, causality broken, time meaningless, everything everywhere all at once. The limits we face are what make reality stable, what make the flow of time, and even life itself, possible. So, the next time you look up at the stars, remember, every beam of light you see is moving as fast as the universe will ever allow. And though we can never match it, we can follow its path, slowly, steadily, beautifully aware that some barriers exist not to imprison us, but to give meaning to the distance between what we are and what we dream to be. To travel just 10% the speed of light, a single ship the size of a bus would require the energy output of the entire planet for a year. It sounds like an exaggeration, a poetic metaphor for the impossible, but it isn't. Physics demands a toll for every increase in velocity, and that toll rises exponentially. Every time you double your speed, you don't just double the energy you need, you multiply it many times over. At low speeds, this cost is manageable. At high speeds, it becomes monstrous. The universe charges dearly for haste. The reason lies in kinetic energy. The faster an object moves, the more energy it stores. At 10% of light speed, that energy becomes staggering. A craft weighing just a few tons would release the equivalent of several thousand nuclear bombs if it were to suddenly stop. To push it that fast requires feeding it the energy of entire nations, maybe entire civilizations. It's not simply a question of technology, it's a question of economics, of feasibility, of survival. Imagine the engineering challenge, a ship powered by all the electricity Earth produces in a year, simply to accelerate to 1/10 of light speed. And that's only half the journey. To stop once you reach your destination, you must spend that energy again, doubling the impossible. It's like throwing a stone across an ocean, but first having to burn a world to make it move. Even if humanity found a way to gather such power, where would we get it? Nuclear reactors, fusion engines, antimatter, all potential sources, yet each carries its own nightmare. Antimatter, for instance, offers unmatched efficiency, but producing a single gram would consume billions of dollars and years of effort. Fusion remains forever, 2 decades away. And chemical fuel, our current champion, can barely lift us out of the solar system. Energy, in the end, is time. The more we spend to move faster, the more time we take to harness it, refine it, control it. The faster we dream of traveling, the slower progress seems to move. It's an ironic symmetry. The race to reach the stars always begins with a crawl. And then there's the danger. At relativistic speeds, the smallest particle becomes a threat. A grain of dust, invisible to the eye, would strike with the force of a bomb. Even the thin gas that floats between stars becomes a wall of radiation and friction. To survive such a journey, a ship would need shielding meters thick, adding mass, demanding still more energy. The cost multiplies endlessly. The universe is patient. It doesn't forbid speed, but it makes it expensive enough to ensure that only light itself can afford it. Every attempt to go faster is a reminder that motion is not free, that acceleration is one of the most expensive currencies in existence. Perhaps that's why our progress has always been measured not by distance, but by understanding. Every equation we solve, every law we uncover, brings us a little closer to knowing why the stars are out of reach. And yet, despite the cost, despite the danger, we keep looking up. Because to dream of going faster is to admit we were never meant to stay still, that the universe may demand everything from us, but we are willing, even now, to pay the price. At relativistic speeds, even a grain of dust becomes deadly. A single collision could release the energy of a bomb, tearing a ship apart in an instant. Between the stars, we imagine emptiness, a clean, pure void. It is filled with the faintest traces of matter, atoms, particles, and specks of interstellar dust drifting in a near-perfect vacuum. A cubic meter of interstellar space might contain just a few molecules, almost nothing. Yet at speeds approaching that of light, those few molecules become shrapnel, and every encounter a potential catastrophe. When a spacecraft travels through air, the atmosphere pushes back, creating drag and heat. In interstellar space, the resistance is almost non-existent, but the consequences of impact are infinitely worse. At just 10% the speed of light, a single grain of dust, no larger than a sand particle, would strike with the energy of a hand grenade. At 50% light speed, it would be more like a missile. And at 99%, it becomes a micro-apocalypse, a high-energy explosion capable of obliterating a ship in an instant. A human crew would never see it coming. The particles are invisible, their motion undetectable until the collision has already happened. The ship would have no time to maneuver, no shield thick enough to absorb the impact. The void between stars, once imagined as a smooth highway of possibility, reveals itself as a minefield of invisible bullets. Scientists have tried to imagine ways to protect against this. Some designs propose magnetic shields, powerful fields that could deflect charged particles before they strike. Others suggest thin layers of vaporized gas ahead of the ship, forming a kind of energy cushion. But dust grains aren't all charged, and even the tiniest neutral ones would slip through. Their energy impossible to deflect without impossible power. To survive decades or centuries of such impacts, a craft would need armor meters thick, armor that would make it too heavy to accelerate in the first place. It's a cruel paradox. To move faster, we must become lighter. To survive moving faster, we must become heavier. Every solution cancels itself. Every fix adds a new flaw. The stars beckon, but between them lies an ocean seeded with invisible knives. Even our robotic probes would not be immune. The proposed Breakthrough Starshot project, tiny, gram-sized spacecraft pushed by lasers to 20% the speed of light, faces this very dilemma. At that speed, a collision with a single dust grain could vaporize the probe entirely. The engineers behind the idea speak of nanoscopic armor, adaptive fields, and statistical luck. But luck is fragile in the cosmos. The universe doesn't bend to optimism, it bends to physics. In the end, interstellar dust reminds us that even in the purest darkness, danger persists. The space between stars is not empty, it's a slow battlefield of particles moving at unimaginable speeds. Each fragment, each mote of dust, is a reminder that distance itself is alive with resistance. Perhaps one day, we'll invent technology capable of sweeping a safe path through the void, a way to glide between stars without tearing ourselves apart. Until then, every dream of interstellar flight must pass through this truth, that even the smallest things can destroy the grandest ambitions, and that in the universe, there is no such thing as truly empty space. Cosmic rays fill interstellar space like invisible bullets. Outside the shelter of the sun's magnetic field, a ship would endure lethal radiation within months. In the quiet black between the stars, danger doesn't always announce itself with sound or motion. It comes instead as silence, particles traveling near the speed of light, relics of ancient supernovae and galactic collisions. These cosmic rays drift through the galaxy endlessly, unseen but deadly. Within the protective cocoon of our solar system, the sun's magnetic field deflects most of them, shielding us from their fury. But the moment a ship crosses that invisible border into true interstellar space, that protection vanishes. What remains is a constant, invisible storm. Cosmic rays are not gentle radiation, like the sunlight that warms our skin. They are fragments of atoms, protons, neutrons, heavy ions, accelerated by the violence of dying stars to energies that defy comprehension. When they strike matter, they don't merely pass through, they tear it apart, shattering molecules, breaking DNA, corrupting electronics. For humans, prolonged exposure would mean radiation sickness, cancer, and eventual death. For delicate instruments, it would mean data errors, fried circuits, and mechanical decay. Our spacecraft, even the most advanced, were never built for such an environment. Beyond the heliopause, Voyager 1's sensors record radiation levels many times higher than those within the solar system. It survives only because its circuits are simple and shielded by the luck of redundancy. But a human ship, a fragile bubble of air and life, would have no such luxury. To survive the cosmic bombardment, it would need walls meters thick, composed of dense materials like lead or water, to absorb or scatter the incoming particles. Yet those very walls would make the vessel impossibly heavy, chaining it forever to the slowest of speeds. Some have proposed magnetic shielding, generating artificial fields strong enough to mimic the sun's own. Others imagine plasma barriers or layers of charged particles surrounding the craft like an energy cocoon. Theoretically elegant, but in practice, these require immense power and precision, far beyond anything we can sustain for centuries of travel. Radiation is relentless. It seeps, corrodes, and accumulates. Against the scale of interstellar time, even the smallest leak becomes fatal. Imagine drifting through that endless dark, the nearest star still 4 light-years away, the sun now just another glimmer behind you. The instruments hum softly, recording data, while a constant hail of invisible particles slams against the hull, unseen yet unceasing. It is the soundless violence of the universe, the quiet hostility of deep space. And yet, those same cosmic rays tell a story. Each one is a messenger from elsewhere in the galaxy, carrying with it the signature of ancient cataclysms. In their destruction, they whisper creation, the echoes of stars that once lived, exploded, and seeded the cosmos with the atoms that became us. The same radiation that threatens to destroy is also what gave us life. Perhaps that's the paradox of space. The duality of awe and danger intertwined. Between the stars, beauty and hostility are the same thing. The light that reaches our eyes, the energy that sustains our world, and the radiation that would destroy us all come from the same cosmic engine. To travel beyond the sun is to step into the raw truth of existence, where protection is gone and the universe meets you barefaced. It is not a place for fragility or fear, it is a place for reverence, for in the storm of cosmic radiation, we glimpse the same power that forged the stars themselves. Between here and Alpha Centauri lies a void so empty that a cubic meter of space contains fewer atoms than a breath of air on the moon. It's hard for the human mind to grasp nothingness. On Earth, even the stillest air is alive with motion, molecules colliding, wind shifting, dust drifting in sunlight. But between the stars, there is no such dance. The interstellar void is the closest thing the universe has to true emptiness. A single cubic meter of that darkness might contain just a few stray atoms, hydrogen, perhaps a whisper of helium, and the occasional grain of cosmic dust, drifting silently through eternity. If you could stand there, though there's no there to stand in, you would be surrounded by a darkness so pure it borders on absolute. This is the ocean that separates every star from every other, vast, silent, patient. It stretches not just across space, but across time. Light crosses it over years, ships would take lifetimes. There is no sound to keep you company, no breeze, no air, no warmth. Even the faint pull of gravity becomes a memory. Between stars, everything is still. You are, for all practical purposes, alone in infinity. And yet, this emptiness is not meaningless. It's the foundation upon which the cosmos is built, the canvas upon which all galaxies are painted. Without the vacuum, there would be no room for stars to shine, no space for planets to form. The nothingness gives shape to everything else. The silence defines the song. The ocean of interstellar space isn't uniform. It ebbs and flows in density like a tide too slow for any creature to notice. Some regions are nearly perfect vacuums, others threaded with faint wisps of hydrogen clouds, the skeletal remains of ancient stars. Every so often, a particle collides with another, a microscopic event that releases a photon, a tiny glimmer of light in the endless dark. Billions of such flickers fill the background of the universe, creating what we call the cosmic microwave background, radiation left over from the Big Bang itself. Even in emptiness, the universe remembers its birth. If you were to travel between the stars, you would cross this invisible sea, gliding through light years of silence. Your engines would hum softly, the faint sound swallowed instantly by the vacuum. Outside the hull, the temperature would plunge toward absolute zero. There would be no dawns, no shadows, only the constant faint glow of distant starlight, a dim reminder that somewhere, warmth still exists. The vastness of this nothingness is humbling. Every atom of your body, every breath you've ever taken, came from stars that burned in defiance of it. Against the infinite black, life feels impossibly fragile, a spark suspended in endless night. And yet, that spark exists because of the void. Without emptiness, there could be no contrast, no creation, no life to gaze back into the dark. So when we speak of the space between stars, we are not describing a gap, but a presence, the quiet architecture of the universe. It is the waiting silence that holds everything together. The nothingness is not absence, it is potential. It is where light travels, where gravity whispers, where time stretches its limbs. The ocean of nothing is not our enemy, it is the universe's breath between heartbeats. And somewhere across that breath, Alpha Centauri waits, a distant spark shimmering just beyond the horizon of the void. Even at 1% the speed of light, the journey would take 4 centuries. For a human crew, it's not a voyage, it's an inheritance passed through generations. Time, more than distance, is the true barrier between the stars. We tend to imagine space as something that can be crossed with enough speed or power, but the truth is harsher. Time stretches it beyond reach. To journey to Alpha Centauri at 1% the speed of light, a velocity far beyond anything we can achieve now, would take roughly 400 years. That's longer than the United States has existed, longer than most civilizations endure. A ship launched in the age of Galileo would still be less than halfway there today. The problem isn't only technical, it's human. Our lifespans, our bodies, even our minds are designed for the scale of a single world. We think in days, years, perhaps decades. We can't easily fathom a project that demands commitment for centuries. A voyage to another star would require not explorers, but descendants. People born aboard the ship, who live and die within its metal walls, never seeing the home their ancestors left or the world their descendants might one day reach. The journey becomes a story passed from parent to child, each generation inheriting a mission that began long before their birth. Imagine such a world, a ship the size of a city, floating in eternal night. Inside, gardens grow under artificial light, water circulates endlessly, and the hum of machinery becomes the background music of existence. The stars outside remain fixed, their motion imperceptible across lifetimes. For the inhabitants, the voyage would feel less like travel and more like exile. The destination would not be theirs, it would belong to their great-great-grandchildren, and perhaps even then, only in myth. Psychologists call this the generational paradox. How do you sustain purpose when success lies centuries beyond your lifetime? How do you keep faith in a destination you will never see? History suggests that belief would fade, replaced by apathy or rebellion or longing for a home that exists only in stories. The mission could fracture, its meaning lost long before arrival. A ship bound for Alpha Centauri could easily become a drifting civilization, cut off from its purpose, worshipping its founders, or forgetting them entirely. And then there's the mechanical toll. No system we've ever built can last that long. Every circuit fails, every seal leaks, every material corrodes. Even the most redundant design would face entropy's slow, patient sabotage. Keeping a spacecraft alive for centuries would require not just technology, but evolution, machines that can repair themselves, or people who can rebuild from the inside out. Time is not kind in the void. Radiation, collisions, decay, and boredom each becomes an enemy when measured in centuries. But perhaps the greatest danger of all is the quiet drift of meaning. Human dreams burn bright but brief, and the stars demand endurance we have never yet proven. And yet, the idea persists. There's something profoundly human about daring to start what you will never finish. To launch a ship knowing it will outlive you is an act of faith, a gesture toward eternity. Maybe that's the real purpose of interstellar travel. Not to arrive, but to remember that we once tried. Because in the end, the struggle against time defines us. We are creatures born to short lives under long skies, forever building things meant to outlast us. Against the scale of the cosmos, our years are mere seconds, but still, we spend them looking forward, trying to outrun the oldest enemy of all, time itself. Science fiction imagines us sleeping through eternity, but biology disagrees. Cells rupture, memories fade, and freezing life may never mean reviving it. In countless stories, the stars are reached not through speed, but through stillness. The crew closes their eyes, the world fades to black, and centuries pass in the space of a heartbeat. When they awaken, another sun shines through the viewport. It's a beautiful idea, humanity defying the long crawl of time by simply sleeping through it. But in the realm of reality, nature is far less forgiving. Cryosleep, suspended animation, hibernation, stasis, whatever name we give it, the goal is the same: to pause life itself. To take fragile, living tissue and place it on hold for decades, maybe centuries, without decay, without loss. The problem lies in the word pause. Life is not a program that can be frozen and resumed. It's a process, a symphony of chemical reactions that must keep playing, even in the slowest rhythm, or it collapses. When water freezes, it expands. Inside cells, that expansion tears membranes and destroys structure. Ice crystals form like tiny blades, slicing through the delicate architecture of life. Scientists have made progress with cryoprotectants, compounds that prevent ice from forming, but these chemicals are often toxic in large amounts. Even if we could cool the human body without physical damage, there's another obstacle: the mind. Memory is not a static object. It's a living pattern of connections, electrical and chemical, constantly shifting. What happens when you turn off the current for 100 years? Nature offers us clues. Some frogs can survive frozen winters, their hearts stopped, their blood thick with glucose to prevent their cells from rupturing. Certain microscopic animals called tardigrades can endure decades without water, entering a state of suspended life so deep that even radiation can't harm them. But these creatures are built for it. Their biology is designed to endure extremes. Ours is not. The human brain, with its delicate web of neurons, evolved to operate within the narrow window of warmth and flow that defines life. Still, scientists dream. Research into therapeutic hypothermia has already allowed doctors to slow metabolism, giving trauma patients precious extra minutes of survival. NASA has studied short-term torpor, cooling astronauts for weeks at a time to conserve energy on long missions. But the leap from weeks to centuries is as vast as the leap from orbit to Alpha Centauri. Even if cryosleep were possible, reawakening may not be. The body could survive, perhaps, but would the person, their consciousness, their memories, ever return intact? The fantasy of cryosleep isn't just about escaping time. It's about our fear of it. It's a refusal to accept that some journeys are longer than a lifetime, that we may never live to see the places we dream of. We imagine freezing ourselves not to cheat death, but to skip the waiting, to leap across the centuries we can't endure awake. Yet perhaps there's a lesson in that longing. Time is the price of awareness. The stars may never feel close enough for one lifetime, but in dreaming of cryosleep, we admit something beautiful, that life, even fragile and fleeting, is precious precisely because it moves forward. To freeze it would be to silence its song. So maybe we are not meant to sleep through the universe, but to witness it, awake, conscious, and temporary, knowing that every second we remain alive among the stars is its own kind of miracle. Some dream of vessels the size of cities, where children's children would inherit the mission. But across centuries, will purpose survive longer than faith? The idea of a generation ship is both visionary and tragic, a world adrift among the stars, carrying not a crew, but a civilization. Inside its vast hull, entire ecosystems would thrive, forests under glass, rivers flowing through artificial valleys, farms lit by suns made of electricity. Its people would be born, live, and die without ever seeing the destination. Alpha Centauri would be a story told in classrooms, a myth passed down like scripture, a promise that only their descendants might fulfill. It's a beautiful dream, humanity escaping the boundaries of Earth by turning the ship itself into a home. But beneath its poetry lies a question older than science fiction itself. Can purpose survive time? To make such a voyage, the ship must be self-sustaining for centuries. Every atom of food, water, and air must be recycled endlessly. Waste becomes resource. Death becomes renewal. Every generation would inherit not just the ship, but the responsibility of keeping it alive. Machines would have to be repaired by hand, power systems maintained by people who never designed them, and culture itself preserved by memory and will. The ship would not merely carry life, it would be life, a closed ecosystem balanced on a knife's edge. But even if we could build it, the true challenge is not mechanical, it's psychological. How do you hold on to a dream when the dreamers are gone? After 100 years, would the mission still matter? Would the descendants of the crew still believe in a destination they would never see? History on Earth offers a warning. Every great vision, from empires to religions, changes with time. Beliefs fracture. Priorities shift. Unity fades into myth. On a generation ship, such loss of purpose could be catastrophic. Imagine a society that begins its journey united by hope, only to drift into doubt. Some might begin to question the mission, to reject the sacrifice of endless waiting. Others might cling to it with zeal, turning it into dogma. Children born in metal corridors might look at the stars outside and wonder why they're still moving, why they cannot choose their own direction. Mutiny, apathy, or even a quiet cultural death could end the journey long before physics does. And yet, the concept endures because it reflects something deeply human, the instinct to keep moving forward, even when the path is longer than a lifetime. In a way, Earth itself is a kind of generation ship, a closed system orbiting a star, carrying billions of souls through the void. Each generation inherits it, shapes it, and passes it on. We are already the crew of a cosmic vessel. We just forget to look out the window. Perhaps that's what a generation ship truly represents, not technology, but trust. Trust that those who come after us will continue the work we began. Trust that meaning can survive beyond memory. A journey to Alpha Centauri in such a vessel would not be about arrival, it would be about endurance, about proving that humanity can persist even without reward. The mission would not just test our science, but our spirit. Can we remain faithful to a dream that only our descendants will see? In the end, a generation ship is less about traveling through space and more about traveling through time. An ark carrying the hope that even in the coldest reaches of the cosmos, purpose can outlive the people who dreamed it. At near light speeds, time slows for travelers, but races ahead for those left behind. This is one of Einstein's strangest gifts to our understanding of the universe. Time is not universal. It bends, stretches, and warps depending on how you move through space. To us, time feels constant, 1 second, one heartbeat, one sunrise after another. But in the fabric of space-time, time is elastic. The faster you go, the more it resists. For an observer traveling near the speed of light, seconds stretch into minutes, minutes into years, and the universe outside races forward like a time-lapse. Imagine a spacecraft departing Earth, accelerating to 99.9% of light speed. On board, the crew might experience only a few years of travel, but when they return, Earth would have aged centuries, maybe millennia. Civilizations would have risen and fallen, continents reshaped, languages forgotten. The travelers would return as relics from the past, strangers in their own future. To them, time would have felt smooth and ordinary. To everyone else, they would have disappeared into myth. This phenomenon, known as time dilation, is not speculation, it's measurable. Astronauts aboard the International Space Station age slightly slower than we do on the surface. GPS satellites, constantly orbiting above Earth, require relativistic corrections to keep their timing accurate. The difference is tiny, fractions of a second, but real. At near light speeds, that difference becomes enormous. Time itself becomes relative to motion. It's a paradox that turns every dream of interstellar travel into a haunting question. For those who make the journey, it may only take a lifetime. For those who remain, the travelers may never return at all. The stars could be reachable, but at the cost of everything left behind. To cross the void might mean to abandon your own era, to become a ghost of time. Science fiction often romanticizes this concept, the lonely Voyager who leaves home for the stars, returning to find their world transformed beyond recognition. But in truth, it's a form of exile. To outrun time is to lose the very context of who you are. The people you love, the world you knew, all gone, replaced by futures you can't imagine. Even if your ship could endure, even if your heart could, the universe itself would conspire to separate you from the past. And yet, there is something profoundly human about this paradox. We are creatures forever torn between motion and memory, longing to move faster, yet terrified of what we'll leave behind. The paradox of relativity isn't just about physics, it's about meaning. It asks us, what is the value of reaching the stars, if in doing so, we lose the world that sent us? Perhaps, in a way, this is the universe's quiet mercy. It reminds us that time binds us not as prisoners, but as participants, that the slowness of life on Earth, the rhythm of seconds and seasons, is what keeps us connected to one another. The faster we go, the more alone we become. And in the end, the stars can wait. Time, after all, is what makes the journey worth taking. To accelerate a single ton to half the speed of light requires more energy than all humanity produces in a year. The barrier isn't distance, it's power. When we imagine space travel, we often think in terms of miles or kilometers, how far a ship must go, how long it will take to get there. But the true enemy of interstellar flight isn't distance, it's energy. Every attempt to accelerate through space comes at a staggering cost. And as we approach the cosmic speed limits imposed by physics, that cost rises beyond comprehension. In space, speed is freedom, but every kilometer per second is a debt that must be paid in fuel. The faster you go, the more energy you need, and the heavier your ship becomes. This is the cruel arithmetic of the rocket equation. Add more fuel, and you add more mass, and you need even more fuel to move it. It's a feedback loop that spirals toward impossibility. At modest speeds, this is manageable. We can send probes to the outer planets, orbit distant moons, and even fling spacecraft beyond the reach of our sun. But when the destination is another star, the numbers collapse into absurdity. To accelerate a single ton to half the speed of light, roughly 150,000 kilometers per second, would require around 5 times 10 to the power of 20 joules of energy. That's roughly the total energy humanity consumes from all sources: coal, oil, wind, solar, and nuclear, in an entire year. For a 1-ton ship, and that's just to speed up, to stop at the destination would demand the same amount again. The energy wall is the universe's quiet warning. It reminds us that momentum isn't free, that motion must be bought with power, and that the cosmic scale demands more than ingenuity. It demands resources on a planetary scale. Even if we harness the full output of the sun, collecting every photon, every watt of its brilliance with vast swarms of solar collectors, it would take minutes, even hours, to gather enough energy to push a small craft to relativistic speed. Some have dreamed of shortcuts, fusion drives, antimatter reactors, even black hole engines. Theoretically, these could unleash energy millions of times more potent than chemical fuel, but each comes with its own impossible cost. Fusion remains elusive, Antimatter annihilation produces near-perfect efficiency, but creating antimatter itself consumes far more energy than it releases. The energy wall doesn't just block us, it mocks us, revealing that the only engine capable of such power already burns in the sky above us. And even if we could solve the energy problem, there's another hidden toll: waste heat. When a ship converts energy to motion, not all of it becomes thrust. Some becomes heat, trapped inside the craft. At interstellar speeds, even a small inefficiency could roast a ship from within. So the question becomes not just how fast can we go. Every step toward the stars demands payment, measured not in dollars or fuel, but in entropy. Perhaps one day, our species will master energy in ways we can't yet imagine. Dyson spheres, quantum converters, fusion chains, all harnessed to drive a single ship into the dark. But until then, the stars remain behind a wall not of distance, but of power. The universe doesn't forbid us from crossing it. It simply demands that we pay in full. And for now, that price is higher than we can afford. For decades, scientists have chased the dream of fusion propulsion. Theoretically, it could cut the trip to decades. Practically, we can't yet make it last a minute. In the heart of every star, nature performs the miracle that humanity has only begun to imitate: fusion. It's the process that powers the sun, the source of all warmth and light we know. In its simplest form, fusion occurs when atomic nuclei collide and merge, releasing energy from the binding forces that hold them together. It's the opposite of fission, the splitting of atoms used in our nuclear power plants. Where fission tears matter apart, fusion joins it, turning a little mass into a vast amount of energy. If we could master this process, it would change everything, from our cities to our spacecraft. The appeal is irresistible. Fusion offers an almost limitless source of clean energy, fueled by elements as common as hydrogen. And for interstellar travel, it promises the holy grail: high efficiency, immense power, and long-duration thrust. A fusion-driven spacecraft could, in theory, reach a significant fraction of the speed of light, cutting the trip to Alpha Centauri from millennia to mere decades. It sounds like magic, but it's just physics, waiting for mastery. The challenge, however, is keeping the reaction alive. On Earth, we've managed to trigger fusion many times, but never to sustain it efficiently. The sun's gravity and pressure do the job naturally, confining plasma, a state of superheated matter, under billions of tons of force. We must replace that with magnets and machines. Devices like tokamaks and stellarators use magnetic fields to trap plasma hot enough to make atoms fuse, but the problem is stability. The plasma writhes like a living thing, unstable and unpredictable. The tiniest disturbance can unravel the reaction, quenching the fire before it truly begins. Even when fusion succeeds for seconds, the energy produced barely matches what we put in. Scientists have come tantalizingly close to net gain, where the reaction gives more energy than it consumes. But practical, continuous fusion remains just out of reach, always 20 years away, as the old joke goes. And yet, the dream persists. Projects like ITER in France and smaller ventures across the world are inching closer, learning how to tame the most volatile force in the universe. Some visionaries imagine compact fusion engines using deuterium and helium-3 that could drive a spacecraft at 10% the speed of light. Others look to advanced concepts like inertial confinement, using tiny pellets ignited by lasers, firing in rapid sequence to produce steady thrust. If even one of these designs worked, it would be a revolution. The stars would still be distant, but not unreachable. A fusion ship could accelerate gently for years, then flip and decelerate for years more, arriving at another star within a human lifetime. The crew would age normally. The journey would no longer require generations, just endurance, courage, and engineering. But as of today, fusion remains a dream of control, of holding a miniature sun in human hands without letting it consume its maker. We know it's possible. The stars prove that every day. What we don't yet know is how to keep the flame steady, to confine power without destruction. Still, it's hard not to imagine it. The soft hum of magnetic fields, the glow of plasma in a chamber, the quiet thrust of a ship powered by starlight itself. Fusion is humanity's promise to the future. The dream that one day we will stop imitating fire and start wielding it. Until that day, we remain here, looking up, chasing the light of the sun, knowing that somewhere deep inside its brilliance lies the secret to our escape. Antimatter offers near-perfect efficiency, but producing a single gram would cost trillions of dollars and centuries of effort. The idea is almost hypnotic, a fuel so potent that matter meeting its mirror image releases energy by direct conversion, E equals mc squared in one incandescent instant. A gram of antimatter annihilating with a gram of ordinary matter would unleash as much energy as dozens of kilotons of TNT. In theory, a tiny pellet of antimatter could hurl a spacecraft to fractions of light speed with a single, meticulously timed reaction. It's the kind of promise that reads like a lullaby for engineers. Sweet, impossible, and dangerous in equal measure. Yet here is where romance collides with reality. Antimatter is not a substance you scoop from a tank or mine from an asteroid. It's born in the violent guts of particle accelerators, created one particle at a time, with staggering effort and cost. Each antiparticle requires more energy to make than it will ever give back if you try to capture it. The process is inefficient by astronomical proportions. For every joule of useful annihilation you might hope to later harvest, you must pour in many, many joules to coax antiparticles into being, separate them from their violent births, and then calm them into storage. The ledger of input and output is brutal. Storage is its own poetry of difficulty. Antimatter cannot touch ordinary matter without vaporizing both in a flash of high-energy gamma rays. To keep it, you must levitate it, in perfect silence, using electromagnetic fields that form invisible cages, cold traps of near absolute zero where antiparticles float alone in vacuum. Penning traps and magnetic bottles hold protons and positrons in laboratories for minutes, hours, sometimes longer. But scaling that delicate dance to kilograms, or even grams, would require rooms the size of cities, cryogenic patients, and error rates so tiny they verge on superstition. A single power glitch, a micrometeoroid, a cosmic ray, and the stored fuel becomes a catastrophic burst of light. Then there's the economics and ethics of creation. Producing antimatter today consumes more energy than humankind uses in a year, for amounts that would be measured in nanograms. The cost is astronomical because every particle must be handcrafted, accelerated, slowed, purified, and sheltered. To talk of grams pushes us into fantastical accounting, trillions of dollars, centuries of focused production, and infrastructure that would dwarf anything civilization has ever committed to peaceably. Even if money were no object, the physics demands time, patience, and a global willingness to concentrate resources on a single, perilous objective. And yet, the idea persists because it reveals something about us, our appetite for elegant solutions, and our willingness to face the impossible. Antimatter sits at the boundary between the theoretical and the practical, a bright shard of physics that shows what a universe of perfect efficiency could look like. It teaches restraint as much as ambition. We study it not because we can use it tomorrow, but because the search clarifies problems: how to store energy, how to control plasma, how to manage extreme heat, that will benefit other, nearer technologies. So antimatter remains, for now, a beautiful ghost in our scientific nursery rhyme. It is a promise we whisper into the laboratory night. Someday, perhaps, we will tame it. Until then, it stands as a reminder that not every brilliant solution is affordable, and that sometimes the most profound advances begin not with conquest, but with the long, patient work of learning what we cannot yet have. Some imagine sails kilometers wide, pushed by lasers or the pressure of sunlight. Elegant, silent, but fragile, one tear could doom a century-long voyage. If rockets are the thunder of our age, Solar sails are their opposite: motion without fire, acceleration without sound. Instead of engines or fuel, they rely on the faint, persistent push of light itself. Every photon that strikes a sail transfers a whisper of momentum, a nudge so small it's almost nothing. But in the emptiness of space, with no drag to slow it, those nudges add up. Day after day, year after year, a ship propelled by light could reach speeds no chemical rocket could ever dream of. The concept is as old as it is poetic. In 1610, Johannes Kepler imagined heavenly ships driven by the wind of sunlight. Centuries later, that vision began to take form. A solar sail works much like the sails of a boat, except its ocean is the vacuum of space and its wind is the radiation streaming from the sun. Or, in more ambitious designs, from powerful ground-based lasers aimed at the sail from Earth. The sail must be enormous, gossamer thin, and flawlessly smooth, capable of reflecting light instead of absorbing it. Even the pressure of sunlight, just 9 micronewtons per square meter, can move mountains if given enough time. NASA's Icaros mission in 2010 and the Planetary Society's Light Sail projects prove the principle works. These tiny spacecraft, no bigger than a box, unfolded sails made of reflective material thinner than a human hair and rode sunlight through space. Their speeds were modest, mere kilometers per second, but their success was profound. They showed that propulsion could be endless, needing no refueling, powered only by the patient hand of the universe. And yet, scaling this idea to interstellar travel is an act of near-mad ambition. To reach even 20% the speed of light, a sail would have to be kilometers wide and weigh almost nothing. It would need to survive the constant bombardment of interstellar dust, radiation, and micrometeorites for decades or centuries without tearing. A single puncture could unbalance its delicate structure, causing it to spin wildly or collapse entirely. Repairing such damage mid-voyage would be impossible. The Breakthrough Starshot initiative dares to dream exactly this. Proposed in 2016, it envisions a fleet of gram-sized probes, each attached to a sail just a few meters across. From Earth, a powerful array of lasers would focus on the sails, accelerating them to 20% of light speed in just a few minutes. At that pace, the tiny probes could reach Alpha Centauri in just over 20 years. But the engineering hurdles are monumental. The laser must remain precisely focused over thousands of kilometers. The sails must withstand acceleration forces tens of thousands of times stronger than gravity. And once the light turns off, the probe must coast through interstellar space, utterly alone, with no way to slow down at its destination. Still, there's something profoundly beautiful about the vision. It transforms travel into patience, engineering into art. The sails would gleam like silver petals unfolding against the darkness, each one carrying a message from its makers, that we learn to move not by conquering the void, but by listening to it. Solar sails may never carry people, but they might carry our first whispers to the stars. They are the poetry of propulsion, the quiet promise that in a universe ruled by fire and fury, even light, gentle and constant, can become a road. Perhaps one day, our descendants will look up and see faint lines crossing the night sky, highways made not of metal, but of starlight itself. Getting there is only half the journey. Stopping at Alpha Centauri would require just as much energy as leaving Earth, a cosmic game of braking with no road. It's a detail that sounds almost trivial until you start to do the math. Reaching another star is already a task of unimaginable effort, propelling a craft across trillions of kilometers of emptiness, accelerating it to a significant fraction of light speed. But once you arrive, what then? You can't simply slow down. There are no brakes in space, no friction, no atmosphere to catch you, no gravity wells to use. Motion continues until something stops it, and in the void between stars, there is nothing. The irony is cruel. The energy required to decelerate a spacecraft traveling at relativistic speeds is nearly identical to the energy it took to accelerate it in the first place. For a journey to Alpha Centauri, that means doubling the impossible, Two monumental burns, one to start, one to stop. Every bit of momentum gained on the way out must be shed before arrival, or else the ship will hurtle past its destination forever, crossing the Centauri system in hours after traveling for decades. The travelers would see their destination sweep by like a mirage, so close, yet unreachable. Engineers have tried to imagine solutions, each one more daunting than the last. Some propose reversing the propulsion system mid-journey, flipping the ship halfway through and firing the engines in reverse for years to slow down. But that means carrying enough fuel for both acceleration and deceleration, a doubling of mass that quickly spirals into impossibility. For chemical rockets, it's hopeless. For fusion or antimatter, it's technically conceivable, but only at costs beyond reason. Solar sails and light-driven craft face their own version of this dilemma. If you use Earth-based lasers to push a sail across the stars, how do you stop once it gets there? The sail can no longer rely on its original light source. It's far too distant. Some theorists suggest that the destination star itself could be used for braking, by angling the sail to catch the faint radiation from Alpha Centauri's suns. But this would take precision beyond anything we can currently imagine, and decades more of gradual deceleration. A misalignment of even a fraction of a degree could send the craft drifting off into the endless dark. Other exotic concepts propose magnetic braking, using immense magnetic fields to interact with the charged particles in the interstellar medium, creating drag. In practice, the density of interstellar matter is so thin that the drag force would be barely measurable. It would take centuries, maybe millennia, to slow down. The truth is that most of our theoretical interstellar missions, like Breakthrough Starshot, don't even plan to stop. Their probes would flash through the Alpha Centauri system in a matter of hours, gathering as much data as possible before vanishing into the distance. A flyby, not a landing. A glimpse, not an arrival. And perhaps that's a metaphor for our place in the cosmos. We move fast, but we rarely linger. We chase the horizon without ever truly touching it. In our haste to reach the stars, we may forget the value of slowing down, of staying long enough to understand what we've found. Stopping, it seems, is harder than going. To come to rest in a universe without friction is to fight motion itself, to wrestle inertia that spans light years. It's the cosmic irony of travel. We dream endlessly of departure, yet the hardest part of every journey is knowing when and how to stop. Even light takes 4 years to reach Alpha Centauri. Any message from a crew would be answered by people who might no longer be alive. It's one of the quietest, most devastating truths of interstellar travel. Communication, our lifeline across the void, breaks down long before the body does. In the vast ocean between stars, distance isn't just measured in kilometers, it's measured in silence. At 300,000 kilometers per second, light is the fastest thing that exists. Yet even it struggles to keep up with the immensity of space. A radio signal traveling from Earth to Alpha Centauri would take 4 years to arrive, and another 4 years for a reply to come back. An 8-year round trip for a single exchange. Imagine trying to hold a conversation like that. You ask a question, and the answer comes after nearly a decade. By the time it arrives, you've changed. The world has changed. The people who sent it may no longer even be there to hear your reply. For a crew traveling across interstellar space, this isn't a delay. It's isolation made permanent. They would leave Earth behind not only in space, but in time. We take instant communication for granted. Messages bounce around our planet in fractions of a second. We can speak face to face with someone on the other side of the world without a hint of lag. But the speed of light, our cosmic speed limit, turns that convenience into impossibility. Between stars, every message becomes a time capsule, a record of the past that can never truly catch up to the present. In practical terms, this means an interstellar crew would be alone. Ground control, mission updates, emergency instructions, all of it would arrive too late to matter. They would be a sovereign world unto themselves, cut off from the authority, comfort, and company of home. Decisions would have to be made without guidance, crises faced without reassurance. It wouldn't just be a test of technology, it would be a test of psychology, of faith, of purpose. Even robotic missions face this barrier. The Voyager probes, still communicating from the edge of interstellar space, already experience hours of signal delay. Each command sent to them is a message to the past, by the time the response returns. For something as far as Alpha Centauri, those delays stretch from hours to years. It's like trying to steer a ship by shouting into a canyon and waiting for the echo to come back years later. And yet, within this isolation lies a strange poetry. Every transmission across space is a kind of time travel. When we receive a signal from a distant star, we're hearing a voice from years ago. When we send one, we're writing a letter to a future that doesn't yet exist. Communication delay is not just a technical problem, it's a philosophical one. It reminds us that the universe does not speak in real time. It speaks in echoes. For the humans aboard a starship, the greatest challenge might not be the journey itself, but the waiting. They would speak to Earth as if to ghosts, sending words that will outlive them. By the time their messages arrive, their children, or their children's children, might be the ones to read them. The voices that answer would belong to strangers who share their DNA but not their time. Perhaps that's the hidden cost of reaching the stars, not just distance, but disconnection. To travel outward is to leave conversation behind. And maybe that's why, for now, we still gaze upward rather than go. And in that silence, we are reminded that the farther we travel from home, the quieter the universe becomes. Radiation, isolation, zero gravity, our biology evolved for Earth. Beyond the magnetosphere, we begin to unravel. Every atom in us is built from the remnants of dying stars, yet the life those atoms formed is exquisitely fragile. We are creatures of balance, made for one atmosphere of pressure, for the steady pull of gravity, for the protection of a planet's magnetic field. We carry the sea inside us in our blood, the weight of air in our lungs, the rhythm of a 24-hour day imprinted in every cell. Out there, beyond Earth's invisible shield, that balance disintegrates. Even a few hundred kilometers above the surface, astronauts begin to feel the difference. The human body was never meant to float. In microgravity, muscles atrophy, bones dissolve, and the heart grows weak from lack of resistance. The fluid that normally settles in our legs drifts upward, swelling faces and pressing on eyes, blurring vision. Over time, calcium leaches from the skeleton, the immune system falters, and wounds heal slowly. Every moment in weightlessness is a quiet negotiation with decay. But physical wear is only the beginning. Earth's magnetic field protects us from the worst of cosmic radiation, a constant storm of high-energy particles born from solar flares and distant supernovae. Step beyond that field, and the onslaught begins. Radiation tears through DNA like invisible bullets, damaging cells faster than they can repair. On long missions, the cumulative dose becomes lethal. The further we go, the less protection there is. On the journey to Alpha Centauri, there would be no shelter but the hull of the ship, and no hull can be thick enough to stop what the universe throws at us. Even if we solved the radiation problem, the psychological toll remains. Months of isolation can warp the mind. Years would erode it. In the silence of interstellar space, with no sunlight, no seasons, no sky, even the most stable psyche would strain. Circadian rhythms would drift, sleep would fragment, time would lose meaning. The crew might live in perpetual twilight, awake but untethered, haunted by the memory of oceans and wind. To survive such a journey, humans would have to become something different. We would need to engineer our bodies to endure radiation, to regenerate bone, to sleep through centuries. Some scientists imagine genetic enhancements, borrowing traits from extremophiles or hibernating animals. Others dream of merging biology with technology, neural implants to stabilize mood, nanomachines to repair cells, cryogenic preservation for the long haul. Each idea edges us closer to a paradox. To reach the stars, we may have to surrender what makes us human. And yet, fragility is not failure, it is our proof of origin. We are soft because our world was kind. Earth cradled us in warmth and air and gravity, and from that comfort, consciousness arose. The very weakness that limits us is also what gives our species empathy, curiosity, and wonder. We look at the stars not because we are strong enough to survive them, but because we are fragile enough to long for them. Perhaps one day we will evolve, or build, or dream our way past these limits. But until then, we remain children of this planet, delicate, temporary, and miraculous. We belong to the gravity that holds us, to the air that wraps around us, to the magnetic field that shields us from the universe's rage. Beyond that invisible line, the cosmos reminds us of a simple, humbling truth. The human body was made to look at the stars, not to live among them. Between stars, there is no sunrise, no horizon, only the endless hum of machinery and the silence of infinite night. It's easy to think of space as adventure, a grand voyage through beauty and mystery. But behind the romance lies a truth colder than any vacuum. Space is not a place meant for life. It is absence made visible. Out there, where the stars are fixed and unblinking, time drifts without rhythm, and the concept of day loses all meaning. There are no landmarks, no skies that change, no sense of motion or progress, just a quiet so vast that even thought begins to sound loud inside your head. Imagine being part of a crew bound for Alpha Centauri, years or decades into the journey. The ship's lights dim to save energy, the engines hum in an endless lullaby. Every corridor looks the same, every view out the window identical, an expanse of stars frozen in place. There is no sunrise to mark the passing of time, no sunset to signal rest. The ship becomes your universe. And the outside, a silent infinity that neither welcomes nor cares. Psychologists already know what even brief isolation does to the mind. A few months aboard the International Space Station can blur mood, memory, and meaning. The absence of sensory change, the monotony of light, sound, and company creates a pressure as real as gravity. In deep space, that pressure becomes absolute. There would be no real-time communication with Earth, no instant voice, no reassurance that someone is listening. Each message would take years to arrive, each reply years more. Conversation becomes history. Companionship becomes imagination. Loneliness in such a place is not just emotional, it's existential. You begin to question not only where you are, but when. The universe outside doesn't change in any perceptible way. The stars are too distant to show motion. The ship's journey through the void feels static. Time moves, but nothing marks it. The line between living and drifting blurs. For the crew, memory might become the only measure of reality, a fragile thread keeping them from dissolving into the sameness of space. Even machines aren't immune to loneliness. Voyager 1, our most distant traveler, sends faint whispers from interstellar space, signals weaker than the background hiss of the cosmos. Each transmission takes nearly a day to reach us. When we reply, it waits another day for our words to arrive. It is a ghost, wandering alone, with nothing but the hum of its own instruments for company. Yet in that loneliness, there is also something beautiful. A kind of sacred stillness. Deep space offers no distractions, no noise, no pretense. It is pure awareness, stripped of everything but the raw encounter between mind and infinity. The silence that terrifies us also invites reflection. In the darkness, you come face to face with the enormity of existence and with yourself. Perhaps the greatest challenge of interstellar travel is not the physics, but the psychology. To venture into deep space is to accept that you may never again hear another human voice in real time. That your heartbeat may be the only rhythm in the void. But it is also to embrace solitude as a mirror, to see, in the vast emptiness, the faint glimmer of meaning that only consciousness can give. For in that boundless loneliness, surrounded by stars that will never speak back, you realize something profound. The silence of the universe is not indifference. It is invitation, a challenge whispered through the dark, asking not whether we can survive it, but whether we can bear to listen to it and still keep dreaming. If humans can't make the journey, perhaps our minds can, sending consciousness encoded in data, traveling as light itself, may outlive our bodies. In the long pursuit of the stars, there comes a point where biology becomes the bottleneck. Flesh is heavy, fragile, and slow to heal. It demands air, food, warmth, and gravity. Data, on the other hand, needs none of these things. In the cold silence between suns, a body would wither, but information could endure forever. So, the question arises, if our physical forms cannot cross the void, could we send something deeper, something of us, instead? The idea of digital immortality begins with a simple premise, that the mind is a pattern, not a thing. Every thought, memory, and emotion is the result of electrical impulses flowing through billions of neurons. If those connections could be mapped precisely, if every synapse could be recorded, then, in theory, the essence of a person could be preserved in data. Uploading consciousness would mean scanning the brain at microscopic resolution, translating the living mind into a model that could run on silicon instead of cells. It sounds like science fiction, but the early seeds of this vision already exist in the work of neuroscientists and AI researchers. Projects today can record the activity of thousands of neurons in real time. Whole insect brains have been simulated, and artificial neural networks can mimic certain aspects of human perception. But a human brain holds more connections than there are stars in the Milky Way, roughly 100 trillion synapses. Capturing all of that with precision, without losing identity or continuity, is far beyond our current reach. Yet progress never sleeps. Every year, the resolution sharpens, the data grows denser, and the boundary between thought and machine blurs a little more. Now imagine what this could mean for space travel. Instead of launching fragile bodies, we could send digital minds, copies of human consciousness encoded into data streams. Light, the universe's fastest traveler, would become our vessel. At a fraction of the cost and none of the risk, a signal carrying billions of minds could be beamed toward another star, racing across the void in just 4 years to Alpha Centauri. There, machines could receive the transmission, rebuild the minds, and perhaps even construct new bodies to house them. We wouldn't need ships. We'd become the signal itself. But this idea also carries unsettling implications. If your consciousness can be copied, are you the one who wakes up on the other side, or just a replica with your memories? Does immortality mean survival or duplication? And if billions of such copies exist, scattered among the stars, which one is truly you? Digital immortality promises freedom from flesh, but it also challenges the meaning of individuality. The same technology that could send us to the stars might dissolve the very notion of self that defines us. We might become a civilization of echoes, fragments of consciousness dispersed through the cosmos, forever aware but no longer human in the way we understand it now. Still, the dream persists because it reflects something ancient in us, the desire to leave a mark that time cannot erase, to live not only as bodies, but as ideas, patterns that endure long after their creators fade. Perhaps one day, the first human to reach Alpha Centauri won't step from a ship at all, but awaken inside a digital dawn, carried there as a whisper of data, traveling at the speed of light. In that moment, the universe will have gained something extraordinary, not a traveler of flesh and bone, but a mind made of memory and light, proof that even when matter fails, consciousness still finds a way to cross the stars. Miniature probes like Breakthrough Starshot promise to reach Alpha Centauri in just 20 years if their sails survive the journey through interstellar dust. When humanity cannot go, our machines go for us. They are our eyes and our memory, our curiosity made metal and wire. The robotic pioneers are not built for comfort or company or return. They are emissaries of thought, hurled into the dark to bring back whispers from the unreachable. In them lies the boldest idea of all, that discovery can outpace the body, that intelligence need not breathe to dream. The Breakthrough Starshot project is perhaps the most daring of these dreams. Announced in 2016, it proposes sending a fleet of nanocraft, each no larger than a postage stamp, to our nearest star system, Alpha Centauri. Instead of rockets, these tiny explorers would ride on beams of light. Gigawatt lasers on Earth would focus on their reflective sails, pushing them to nearly 20% of the speed of light. In just a few minutes, they'd be moving fast enough to cross the distance between stars in roughly 20 years. It would be the fastest, farthest leap any human creation has ever made. At that speed, Alpha Centauri becomes not a fantasy, but a destination, close enough to reach within a human lifetime. But the journey would be perilous. The interstellar medium, empty as it seems, is filled with dust and microscopic debris. At 1/5 the speed of light, even a speck of dust carries the energy of a bullet. A single collision could vaporize a probe in an instant. Engineers must therefore design sails that are both impossibly light and incredibly tough, thin enough to ride on photons, yet strong enough to endure decades of bombardment. Then there's the problem of aiming. To hit a target 40 trillion kilometers away with a laser beam requires accuracy beyond anything we've ever achieved. The slightest misalignment could send the probes careening into the void, missing their destination by light years. And even if they survive, their arrival will be brief, a flyby lasting just hours. With no way to slow down, they'll race through the Alpha Centauri system at blinding speed, snapping images and collecting data before vanishing forever into the dark. Communication, too, is a riddle. Each probe signal, weaker than a household light bulb, must travel back across 4 light-years of empty space. Receiving it would require the most sensitive instruments ever built, capable of listening to the faintest whisper through the cosmic static. For every byte of data, we'd wait years. And yet, even a few images, a glimpse of alien suns, a hint of planets, would redefine our place in the cosmos. Despite the obstacles, the vision of robotic pioneers carries a quiet grace. These probes would not just be machines, they would be humanity's first interstellar thoughts made real. They would represent a kind of immortality, not of flesh, but of curiosity. For billions of years, life has been bound to its homeworlds. But when those tiny sails unfurl and catch the light, something changes. For the first time, the universe will contain not just stars and planets, but artifacts of intelligence moving between them. A conversation between galaxies begins, one side spoken in light, the other in silence. Perhaps, centuries from now, when our descendants finally follow in person, they will find these robotic scouts drifting quietly through the Centauri system, ancient, scarred, but still carrying the message of their creators. We were here. We dared to reach you. And in that message, written in the language of photons and persistence, the universe will hear the truest expression of what it means to be human. Not to conquer the stars, but to send a piece of ourselves ahead to keep the dream alive until we arrive. Every great mission begins with optimism and ends with compromise. The dream of reaching another star might be the most stubborn hope we've ever had. Hope is the engine that has carried humanity further than any machine ever could. It is what drove the first explorers to sail across unknown oceans, what pushed us to climb mountains, cross deserts, and one day, reach the moon. Every boundary we've broken began as a dream that refused to yield to reason. And yet, hope is also fragile, brilliant in its ignition, but easily dimmed by the weight of reality. For all our ambition, the stars remain distant not because we lack imagination, but because the universe is mercilessly honest about what is possible. Every generation rediscovers this tension between wonder and limitation. In the 1960s, we looked up and believed we would soon walk on Mars. Decades later, we're still dreaming, still preparing. Each advance brings new obstacles, budget cuts, political shifts, technological ceilings. Every spark of progress flickers against the cold wind of practicality. Interstellar travel, more than any other pursuit, embodies that fragile balance. It asks for faith not just in physics, but in ourselves. Hope, in this context, isn't naive, it's defiant. It persists in the face of impossibility. The scientists sketching designs for fusion engines and antimatter reactors know how far away success really is. The dreamers building solar sails know that a single error could undo decades of work. And yet they continue, because the act of trying, of refusing to accept that too far means never, is its own kind of victory. But hope alone is not enough. History shows that the longer a mission stretches, the easier it is for purpose to blur. The initial spark gives way to slow attrition, and the extraordinary becomes routine. When goals outlive the people who conceived them, what sustains belief? A journey to Alpha Centauri, spanning decades or centuries, would test not just engineering but culture itself. It would demand that hope become inheritance, that belief be passed on like a torch from generation to generation. That torch, though, burns unevenly. Across centuries, priorities shift. A crew, born into a mission, might not share the faith of those who launched it. They might see the goal as myth, or burden, or even imprisonment. Without shared purpose, hope splinters into factions, cynicism, and decay. The ship that was once humanity's beacon could become its tomb, a drifting monument to ambition undone by time. And yet, there is a reason the dream refuses to die. Every telescope we build, every probe we launch, every grainy photograph of distant worlds reminds us that hope, though fragile, regenerates. It is contagious. Each discovery reignites it. The light of a single exoplanet glimmering around another star can rekindle the belief that somewhere, somehow, the impossible might yet unfold. The fragility of hope, then, is not a flaw. It is what makes it precious. Because every time we face the abyss and choose to keep dreaming, we reaffirm what it means to be human. We were never promised the stars, yet we reach for them anyway. Perhaps that's the true beauty of this endless pursuit. Even if we never set foot on another world, even if Alpha Centauri forever remains beyond our grasp, the act of trying binds us together across generations. Hope may be fragile, but it is also self-renewing. Like starlight, it travels through the dark long after its source has faded, reminding the universe that somewhere, against all odds, a species dared to dream. There's not just one star, but three: Alpha Centauri, A, B, and Proxima. When we look up at Alpha Centauri from Earth, it appears as a single bright point, a lonely beacon just beyond our reach. But through a telescope, that single gleam divides into a system of three suns locked in a graceful, gravitational dance. Alpha Centauri A and B are a binary pair, circling one another every 80 years, while the faint, red Proxima orbits them both from a vast distance, like a quiet observer on the edge of a cosmic ballroom. Together, they form a family of fire, a triad of light that has burned for longer than our species has existed. Alpha Centauri A is much like our Sun, yellow-white, warm, and steady. Its companion, Alpha Centauri B, is slightly smaller and cooler, with a more orange hue. Their relationship is a delicate balance between attraction and separation. At their closest, the two stars are about as far apart as the distance between the Sun and Saturn. At their farthest, as wide as the gap to Pluto. Their mutual orbit is a cosmic waltz measured not in days or months, but in human lifetimes, an eternal dance of gravity and grace. Then there is Proxima Centauri, the faintest, smallest, and nearest of the three, though it trails far behind, drifting more than 13,000 times the distance between Earth and the Sun. It is technically the closest star to us. A dim red dwarf, Proxima is a restless ember, prone to violent flares and bursts of radiation. To the naked eye, it's invisible from Earth, yet its quiet persistence makes it a kind of cosmic paradox, the smallest star, and yet the nearest one we have. Around Proxima orbits a planet that has captured the world's imagination, Proxima b. Roughly the size of Earth, it sits in the habitable zone, where liquid water might exist. It could be a rocky world bathed in faint crimson light, its days and nights locked to its star, one side forever scorched, the other eternally frozen. Whether it harbors oceans or atmosphere, no one yet knows. But its presence alone transforms Alpha Centauri from a distant curiosity into a potential destination. To imagine standing beneath such a sky is to dream beyond familiarity. On a world orbiting Alpha Centauri A or B, there would be no true night, only shifting glows as one sun sets and the other rises. Shadows would bend in opposite directions, colors would bleed into each other, and the rhythm of light would never cease. The very concept of day would dissolve into a choreography of golden and orange fire, moving in time with the heartbeat of the system itself. These three stars have endured together for billions of years, bound by gravity's invisible thread. Their dance has survived cosmic collisions, galactic tides, and the birth and death of other suns. Long before humanity learned to dream of them, they were already entwined, proof that stability and chaos can coexist in cosmic harmony. Perhaps that's why Alpha Centauri captures our imagination so deeply. It's not just a system of stars, it's a mirror of our own longing. Three suns, orbiting in endless balance, remind us that even in the vast emptiness of space, companionship endures. They are a celestial family, holding together through time and distance, whispering across the void that not everything beautiful must be solitary. When our telescopes gaze their way, they see not just light, but history, a waltz written in gravity, a story still unfolding. And somewhere in that slow cosmic rhythm lies the quiet possibility that one day we may join the dance ourselves. Orbiting in the habitable zone of its faint red sun, Proxima b could have oceans or nothing but rock and radiation. It's the closest home we'll never see. When astronomers discovered Proxima Centauri b in 2016, the world seemed to collectively hold its breath. For the first time, we had found a planet orbiting the star nearest to our own, a world just 4.24 light-years away. Close enough, in cosmic terms, to imagine, close enough to tempt the mind into wandering. Could there be clouds above its surface? Could winds sweep across alien seas beneath a crimson sky? Or is it a barren, hostile world, an echo of our hopes more than a reflection of our home? Proxima b orbits its parent star every 11 days, tucked within what we call the habitable zone, the region where temperatures might allow liquid water to exist. That simple phrase, liquid water, is the fulcrum of all our searching. Where there is water, there may be chemistry, and where there is chemistry, there may be life. But orbiting a red dwarf is no easy existence. Proxima Centauri is a dim, turbulent star, smaller and cooler than our Sun, but prone to violent outbursts of radiation. A flare from Proxima can be hundreds of times more intense than anything our Sun emits. For any planet nearby, that means a constant bombardment of charged particles and ultraviolet light, stripping away atmospheres, sterilizing surfaces, and turning oceans, if they ever existed, into vapor. If Proxima b once had an atmosphere, it may be long gone. Without protection, its surface could be scorched by radiation during the day and frozen in perpetual darkness on the other side. Because the planet is likely tidally locked, always showing the same face to its star, one hemisphere would be eternal daylight, the other eternal night. The line between the two, the twilight zone, known as the terminator, might be the only place where temperatures are stable enough for liquid water to persist, and where life, if it exists, could cling to a narrow band of survivability. Yet the possibilities are not all bleak. If Proxima b somehow retains a magnetic field, stronger than Earth's, it could deflect some of the stellar wind. If it has an atmosphere thick enough to circulate heat between hemispheres, then even a tidally locked world might breathe. In that case, it could harbour vast oceans of liquid water beneath crimson skies, glowing faintly under the pale warmth of its star. To the human eye, the daylight there would be strange, soft and dim, more like the glow of a dying ember than the brilliance of our sun. From such a world, the night sky would be extraordinary. Alpha Centauri A and B would blaze brightly, twin suns suspended in the distance, each one far larger and whiter than any star we see from Earth. Our own sun would appear as just another pinprick of light among billions, a single spark in the cosmic sea. We can't yet see Proxima b directly. It's too faint, too small, too close to its sun. What we know comes from the subtlest of wobbles in the starlight, tiny shifts that reveal its presence like a whisper caught in a wind. But in those wobbles, in those infinitesimal signs, lives a dream older than language, the hope that we are not alone. If life does exist there, perhaps microbial, perhaps complex, it has been evolving under an alien sun for billions of years, untouched by our presence. It would not know us, nor we it, except as two species sharing the same cosmic neighborhood, separated by a gulf that even light takes years to cross. Proxima Centauri b is close enough to remind us that the stars are not unreachable, but far enough to show us that imagination still outpaces our technology. It is both promise and impossibility, hope and humility in equal measure. We may never walk its surface or breathe its air, but knowing it exists changes everything. Because somewhere, just beyond the edge of our sky, there is another world, waiting, silent, and shining in the faint red glow of its lonely sun. 4 light-years feels near, but in human terms, it's beyond comprehension. Even our most advanced technology hasn't left the cosmic doorstep. We speak of Alpha Centauri as our neighbor, as though it were just down the cosmic street, a mere hop across the interstellar fence. But the universe has a way of disguising immensity as intimacy. 4 light-years may sound small, almost manageable, until you try to measure it not in light, but in human terms, in years, in effort, in endurance. Then the illusion shatters, and distance reveals its true nature, merciless, absolute, and endless. Consider this: light, the fastest thing in existence, traveling at nearly 300,000 kilometers per second, takes more than 4 years to reach Alpha Centauri. A radio signal, a beam of laser light, even the flash from a nuclear explosion, all would need the same time to bridge that gap. For comparison, the signals that guide a Mars rover take minutes to cross the void. To talk with a probe at Alpha Centauri would take 8 years for a single exchange, a conversation that moves slower than history itself. Now, imagine crossing that distance physically. The fastest spacecraft ever launched, NASA's Parker Solar Probe, travels at about 700,000 kilometers per hour, fast enough to circle Earth in just over 3 minutes. Yet at that speed, it would take over 6,500 years to reach Alpha Centauri. Voyager 1, humanity's farthest traveler, has been sailing through space for nearly half a century and has only moved 0.002 light-years from home. At this rate, it would need 75,000 years to reach our nearest star. In all our brilliance, all our fire and ambition, we've barely stepped off the front porch of the Milky Way. When we say 4 light-years, our minds shrink the meaning. We imagine lines on a map, numbers on a chart. But space is not a map. It's a void where time itself stretches into geometry. The human brain evolved to understand rivers, mountains, and oceans. Not distances so vast that light, our ultimate measure of speed, becomes the only unit that makes sense. The gap between Earth and Alpha Centauri isn't just physical, it's philosophical. It's the difference between what we can imagine and what the universe is. Even in the age of telescopes like James Webb, which can peer billions of years into the past, the stars that seem so close are still impossibly far. Alpha Centauri's light, the gentle shimmer we see on warm nights, left that system before smartphones existed, before the internet, before the first exoplanet was even discovered. When we look at it, we're seeing history already 4 years old, a celestial postcard still en route. And yet, the illusion of closeness is what keeps us reaching. It's what drives us to build faster ships, larger telescopes, and more daring dreams. Because if the nearest star feels almost within reach, then maybe, just maybe, the next one will be closer still. The irony of the cosmos is that distance defines everything, yet it's closeness that drives us forward. Alpha Centauri taunts us from the horizon, bright enough to stir hope, distant enough to humble it. 4 light years, a heartbeat to the universe, an eternity to us. But perhaps that's the lesson hidden in the illusion, that the journey itself, not the arrival, is where meaning lives. We may never reach our neighbor's door, but we'll keep walking toward it anyway, step by impossible step, until one day, even light will have to look back and marvel at how far we've come. Warp drives, wormholes, and space-time manipulation. Concepts born not of engines, but equations. All remain imprisoned by energy demands that border on the impossible. When imagination reaches the end of engineering, theory takes over. Physicists, poets, and dreamers alike have peered into Einstein's equations and found hints of extraordinary loopholes, ways to cross vast distances without ever truly moving through them. Warp drives that bend space-time like fabric, wormholes that tunnel shortcuts through the universe, and exotic fields that could twist reality itself. On paper, they promise to turn light years into moments. In practice, they remain fantasies wrapped in mathematics. The most famous of these is the Alcubierre drive, proposed in 1994 by Mexican physicist Miguel Alcubierre. His insight was elegant and bold. If nothing can move faster than light through space, perhaps we could move space itself. The idea is simple to imagine but profound in consequence. A spacecraft wouldn't travel forward in the conventional sense. Instead, it would sit within a warp bubble, a pocket of space-time that contracts in front of the ship and expands behind it. The ship, resting inside this bubble, wouldn't technically move at all relative to its immediate surroundings. Sidestepping the laws of relativity, the universe would move around it. In this framework, interstellar travel could, in theory, happen at apparent speeds faster than light. Alpha Centauri could be reached not in thousands of years, but in weeks. But the universe rarely gives away its secrets so easily. The equations demand something exotic, negative energy, a form of energy density lower than the vacuum itself. No known material possesses such a property. It's as though the drive requires a kind of anti-gravity fuel, a substance that defies every law we know. Calculations suggest the amount needed to move even a small ship might equal the total energy output of an entire star. Other ideas reach even deeper into the cosmos's strangeness. Wormholes, predicted by the mathematics of general relativity, are shortcuts between distant regions of space-time, tunnels through the fabric of reality itself. If they could be stabilized and expanded, one end could be placed near Earth, the other near Alpha Centauri. A traveler could step through and emerge 4 light-years away in an instant. But like warp drives, wormholes demand negative energy to remain open, lest gravity collapse them into oblivion. They are as fragile as they are fantastic, possible in theory, but unbuildable in practice. Quantum physics adds its own curiosities: vacuum fluctuations, quantum foam, and space-time metrics that ripple at unimaginable scales. Some theorists believe that advanced civilizations, billions of years older than ours, might have learned to manipulate these forces, bending the universe like clay. But to us, they are still whispers in the math, beautiful, unsolved, and untouchable. And yet, these impossible ideas serve a purpose. They expand our boundaries, not by breaking the laws of physics, but by exploring their edges. They remind us that the universe is not closed to wonder. What seems impossible today may simply lack a language to describe it. In truth, warp drives and wormholes may never leave the realm of imagination, but imagination is itself a kind of propulsion. It accelerates understanding, even when engines cannot. The equations that describe space-time are not merely limits, they are invitations to look deeper, to question, to dream. For now, The path to the stars still lies along the slow road of light and patience. But every equation scribbled in defiance of that speed limit is a candle in the dark, a quiet rebellion against the vastness that keeps us homebound. And someday, when physics evolves beyond our current reach, perhaps one of those candles will become an engine, and the universe will finally open its doors. Each new advancement reveals the same truth. The universe is not built for travel, it's built for patience. For all our ambition, every breakthrough in physics seems to end the same way, with awe and resignation. The universe doesn't rush, it expands, evolves, and decays in rhythms that make our centuries seem like seconds. Its distances are not obstacles, they're design. Every star, every galaxy, every atom of the vacuum conspires to remind us that motion, on a cosmic scale, is slow. Painfully, beautifully slow. When humans first looked up at the night sky, we imagined it as a ceiling, a firmament just beyond the clouds. Later, we learned that the stars are suns, that the dark between them is not air but emptiness. We built engines and equations, rockets and theories, and each one brought us closer to understanding what we were truly up against. The problem was never technology. It was time. To cross even the smallest interstellar distance requires an endurance our species has never known. Every advance brings us closer, yes, but also humbler. Fusion propulsion might cut the trip to decades, but not within a lifetime. Antimatter promises efficiency, but demands energies greater than Earth can supply. Warp drives shimmer in the equations, but collapse under the weight of their own requirements. Each discovery brings us face to face with a quiet cosmic irony. The more we understand, the more we realize how perfectly the universe resists being crossed. Perhaps that resistance is not cruelty, but balance. Motion at our scale must cost something, otherwise meaning would erode. If the stars were easy to reach, they would not hold the same power over us. The longing itself, the ache of distance, is what gives them beauty. The struggle to reach them defines our species more than a rival ever could. Patience, then, becomes not defeat, but wisdom. The universe measures progress in light years, but we measure it in persistence. The first sparks of fire, the first metal tools, the first rockets breaking the sky, all are steps on a single, unbroken path. And though we may never live to see its end, the path itself is sacred. Every invention, every failed experiment, every dream of a ship sailing on starlight adds another heartbeat to the great rhythm of becoming. There's a serenity in that realization. The cosmos is not a race, it's a conversation, one that unfolds over eons. Our role is to listen, to learn, and to take our turn in the dialogue of discovery. The silence between stars is not rejection, it's invitation. An invitation to slow down, to see the grandeur not just in destinations, but in the journey itself. So we wait, and we dream, and we build. Because maybe the universe doesn't reward speed at all, maybe it rewards endurance. And in our small, fragile way, we are learning that patience is not the absence of motion, but the purest form of it. After all, every photon that leaves a distant star travels for millions of years before finding a single pair of eyes to see it. Perhaps, like that light, we too are meant to wander slowly, our brilliance shining not in how fast we move, but in how long we last. We dream of escape, but gravity, radiation, and physics themselves form invisible walls around our solar home. For all our wonder, humanity lives inside a gilded cage, vast, radiant, and inescapable. The solar system feels infinite compared to our small blue world. Yet in truth, it is just one cell within the cosmic labyrinth. Every law of nature that makes life possible also confines it. Gravity keeps us grounded, but it also chains us to our sun. Radiation warms our world, yet beyond the magnetosphere, it becomes a storm of death. Even light, our messenger across the void, reminds us that freedom has a speed limit. The universe, it seems, allows no easy exit. To leave Earth is already an act of defiance against gravity's grip. Every launch is a delicate negotiation with physics, a struggle between energy and inertia. Rockets must burn mountains of fuel to gain mere minutes of weightlessness. The escape velocity from Earth is over 11 kilometers per second. From the Sun's gravity, it's 617. Every planet, every moon, every orbit adds another layer of resistance, and beyond that lies an even subtler cage, the vastness itself. The distances between stars are so immense that even light takes years to cross them. For matter, for bodies made of atoms, those gulfs might as well be eternal. The deeper we go, the more the cage reveals its bars. Radiation becomes a constant assault, particles streaming through metal, through flesh, through memory. Outside Earth's magnetic field, astronauts would face doses of cosmic rays 100 times higher than on the surface. A few months might be survivable. A few years would be ruinous. Without thick shielding or the embrace of Earth's atmosphere, our DNA unravels. Space is not empty, it's poisonous. Even time conspires against escape. Relativity ties motion to mass, and mass to energy. The faster we try to flee, the heavier we become. To approach the speed of light would require infinite energy, an impossible ransom. They are the walls of our cosmic cell, written not in stone, but in space-time. And yet, prisons are defined not only by their walls, but by the longing they inspire. We have stared through these invisible bars for millennia, dreaming of what lies beyond. Every invention, telescopes, rockets, probes, is a scratch on the glass, a mark of rebellion. Voyager 1, now billions of miles away, carries a golden record inscribed with our music, our greetings, our hope. It has not escaped the sun's gravity, it never will, but it has crossed the heliopause, the border where the solar wind fades into the true interstellar night. Even from that distance, the sun still holds it by a thread. Perhaps the cosmic prison is not punishment, but protection. Within these boundaries, life evolved, flourished, and became self-aware. The same forces that confine us are the ones that shaped us. Without gravity, we would never have oceans. Without the sun's radiation, we would never have warmth or growth. Even the vacuum of space, so cruel to the body, is what allows stars to shine and galaxies to form. The walls that imprison us are also the architecture of our existence. Still, the yearning persists. To look up at the night sky is to feel the tension between safety and freedom, the sense that we were born into both sanctuary and captivity. The universe, vast and silent, seems to whisper, "You may go as far as you dare, but not yet beyond." Maybe one day we'll find the key. Maybe the prison will turn out to be an illusion, a limitation of perception, not physics. But until then, we live in a paradox, bound by the same laws that give us life, dreaming always of the space beyond the bars. And perhaps that's what makes the dream so powerful. The cage may be cosmic, but the longing for freedom, that restless spark that makes us look to the stars, is something even the universe itself cannot contain. Maybe we reach Alpha Centauri not through engines, but through understanding. Through telescopes, we already touch its light, 4 years delayed, but real. There's a quiet truth hidden in the night sky. Our minds travel faster than our bodies ever will. Long before rockets, long before equations, long before we even had words for the stars, humanity was already reaching them through imagination. Thought has no mass, no momentum to resist, no gravity to escape. It moves freely across the cosmos, carried by curiosity. And in that sense, we have already made the journey to Alpha Centauri countless times. When you gaze at that small, golden point of light in the southern sky, you are not seeing it as it is, but as it was 4 years ago. Every flicker of brightness your eyes perceive began its journey before the present moment, a message in flight across the abyss. That light has crossed trillions of kilometers, untouched, unbroken, to reach your retina. It carries with it the story of 3 suns intertwined in orbit, the warmth of their fusion, the history of their dance. In a very real sense, Alpha Centauri is already here, etched into the photons streaming into your eyes. The only delay is time itself. That's the beautiful irony of our limitations. While our bodies remain trapped by distance, our minds are already interstellar. Telescopes extend our senses beyond anything evolution could have imagined. Through them, we've mapped exoplanets orbiting distant suns, traced the birth of galaxies, and witnessed the afterglow of creation itself. The James Webb Space Telescope, orbiting silently in the cold, has seen galaxies so far away that their light began its journey before Earth existed. In its mirror, the universe reveals itself not as distant, but as connected, woven together by light and time. Perhaps reaching Alpha Centauri, or any other star, isn't about physical arrival at all. Perhaps it's about comprehension, the ability to hold something so distant within the boundaries of awareness. When we measure its light, decode its composition, map its planets, and understand its orbit, we are already touching it in the only way that matters. We are turning distance into meaning. Humanity's greatest voyages have never been purely physical. The real leap has always been in perception, in how far we can stretch the boundaries of the mind. The speed of thought is infinite because it travels through imagination, not space. Every discovery, every question, every dream of what might exist beyond our sky is a step closer to those distant suns. And yet, this doesn't make the dream of travel meaningless. On the contrary, it deepens it. The light that took 4 years to arrive becomes something intimate, personal, and alive within consciousness. When you close your eyes and picture its red and gold stars orbiting one another in silent grace, you have, in a way, already arrived. Perhaps this is how humanity will truly conquer the stars, not by breaking the laws of physics, but by expanding the universe within the mind. Every telescope, every equation, every thought that bridges the distance between what we can see and what we can understand is a kind of voyage, a journey not through space, but through awareness. Because in the end, the mind itself is a spacecraft, massless, tireless, eternal, in its curiosity. It needs no engine, no fuel, no trajectory. It simply looks up, and suddenly, it is everywhere. Every photon from Alpha Centauri is a message from 4 years ago. When we look at it, we're watching history written in starlight. The night sky is not a view of the present, it's a window into memory. Every glimmer, every faint twinkle is a story delayed by time. The universe has no now as we know it. Light takes too long to cross its vastness. So, when we gaze at Alpha Centauri, we are not seeing what is, but what was. The light striking your eyes tonight left that system 4 years ago, long before this moment existed. To see the stars is to read the past as it unfolds in slow motion, stretched across the fabric of space. It's a strange, humbling thought. Every photon of starlight is a traveler. It left the surface of a sun, crossed interstellar space, and slipped through the thin veil of our atmosphere to arrive at you, softly, silently, perfectly intact. Those tiny packets of light have survived cosmic radiation, gravity, and time itself. They carry information about the temperature, motion, and chemistry of their source, like cosmic fingerprints. When astronomers analyze that light through prisms and sensors, they can reconstruct entire worlds, planets orbiting unseen, atmospheres rich with vapor or gas, even hints of weather on alien horizons. The past, written in color and spectrum, becomes the foundation of our understanding. And as we look outward, we are also looking backward. The farther we see, the older the light becomes. The galaxies captured by the James Webb Space Telescope shine from billions of years ago, from a time when the universe was still young and wild, when the first stars were kindling in the dark. In that sense, astronomy is not just the study of the heavens, it is the archaeology of time. Every observation is a form of time travel, every telescope a bridge between eras. This cosmic delay, this stretching of the present, is more than just a scientific fact. It's a lesson in perspective. The light we see from Alpha Centauri tonight began its journey before our recent history even unfolded, before our current dreams, our triumphs, our failures. It reminds us that time is both fragile and vast, and that our now is only a thin layer floating atop an ocean of moments already past. And yet, there's something comforting about this slowness. The light from our sun is already 8 minutes old. The glow of Jupiter takes nearly an hour to reach us. Even in our own solar system, the universe demands patience. Time, it seems, is not an obstacle, but a rhythm, one that the cosmos plays with perfect composure. When we look to Alpha Centauri, we are witnesses to a 4-year-old event still unfolding in our sky. Somewhere, at this very instant, those stars are shining in their present, sending out new light that will not reach us until 4 years from now. Our future is already glowing there, unseen but inevitable, a message in transit, written in photons, heading our way. In that sense, to look at the stars is to live both in the past and the future. We are the only creatures we know who can stand in one moment, perceive another, and understand the gap between them. That awareness of distance, of time, of patience is what makes us cosmic beings, not just terrestrial ones. So the next time you look at Alpha Centauri, remember, the light you see tonight began its journey when you were someone slightly different, living in a slightly different world. And 4 years from now, a photon leaving that same star now will arrive here to meet the person you will become. In that silent exchange, across time and distance, the universe whispers its most poetic truth. Every act of seeing is also an act of waiting. Even if we never arrive, the attempt itself defines us. To dream beyond reach is to remind the cosmos that we are awake. There is something profoundly human about chasing what we cannot catch. We build machines to touch the edge of the possible, send our thoughts where our bodies cannot go, and shape stories out of distance itself. The dream of reaching Alpha Centauri is not just a scientific pursuit, it is an act of defiance against limitation. Every generation before us has stared into the dark and asked the same question: how far can we go? Each answer has pushed the boundary of imagination a little further outward. The journey matters because it is not really about the destination, it's about transformation. The moment we decided to try, we became something new, a species aware of the scale of the universe and unafraid to engage with it. Even if no ship ever sails between the stars, the mere desire to do so has changed us. It has forced us to understand energy, gravity, and time on deeper levels than ever before. It has led us to build telescopes that can peer into the dawn of creation, to craft engines that push against the void, to write equations that challenge the limits of physics itself. The dream may be unreachable, but the striving has already rewritten our story. Perhaps that's what the universe expects of intelligence, not conquest, but curiosity. The cosmos is vast beyond measure, filled with cold silence and infinite waiting. Yet in that silence, we are the brief spark that asks why. To dream of Alpha Centauri is to announce to the universe that consciousness has emerged here, that life has grown bold enough to look beyond its cradle. Whether we succeed or fail almost doesn't matter. The act of trying is the message. Every rocket launched, every probe sent into the unknown, every beam of light aimed at another star is a form of conversation. It says, "We see you. We know you're there. And though we may never touch you, we will never stop reaching." That reaching is the essence of who we are. It's in our art, our science, our faith, and our restlessness. It's the same impulse that drew our ancestors across oceans and deserts, that taught us to build from stone and flame. The dream of the stars binds every human endeavor into one story, the story of a species learning to look up and see possibility instead of emptiness. Even if no ship ever leaves the solar system, even if Alpha Centauri remains forever just out of reach, the yearning itself gives shape to meaning. Because what matters most is not whether we arrive, but that we begin. The journey to another star may never be completed, but it already defines us. It is the quiet promise we make to every generation after us, that we will keep exploring, keep imagining, keep dreaming of horizons beyond sight. For in the act of dreaming, we prove something no equation can express, that we are not asleep in the dark. We are awake, and we are listening. Perhaps, somewhere near Alpha Centauri, another intelligence looks toward our faint yellow sun, asking the same impossible question we do tonight. It's easy to imagine ourselves as the lonely observers of the cosmos, tiny, fragile creatures staring upward from a pale world, wondering if anyone else is doing the same. But what if we're not alone in our wondering? What if, at this very moment, another consciousness circles one of those distant suns, looking toward us with the same curiosity, the same ache for connection? Somewhere, 4.37 light-years away, our sun glimmers in their night sky, a small, golden point among countless others, and perhaps they too feel the pull of its light. For all we know, they could be as advanced as we dreamed to be, or as primitive as we once were. Maybe they have oceans that mirror the red glow of Proxima's light, or skies painted by two suns rising together in amber harmony. Maybe they built their own instruments, their own telescopes, to pierce the void and trace the faint, rhythmic pulse of a small yellow star on the galactic horizon. And maybe, when they found it, they felt the same quiet awe, the realization that the universe might be full of watchers watching each other. The thought is both comforting and unsettling. Every signal we send into the dark, the radio waves, the whispers of television, the coded hum of our spacecraft, spreads outward like ripples in a cosmic pond. Some of those ripples are already passing through the Alpha Centauri system, carrying with them the echoes of our music, our wars, our laughter. To any ears attuned to listen, Earth would not be silent. Our civilization, from the moment we invented radio, began announcing itself to the stars. Perhaps those signals have already been heard. Perhaps they have not. The silence that greets us may be evidence of emptiness or of patience. Maybe the universe is teeming with life, but each civilization waits, listening, afraid to speak first. We call this the Great Silence. But maybe it's not silence at all, just a symphony too vast and slow for us to perceive. And yet, the possibility that someone might be looking back changes everything. It transforms the stars from destinations into mirrors. The questions we ask of the cosmos, are we alone? Are we special? Are we ready? Might already be echoing from another world. In that symmetry of curiosity lies something deeply profound, connection without contact, kinship without meeting. Two minds, separated by light years, both daring to wonder. It's humbling to think that as we look toward Alpha Centauri tonight, we might be part of a mutual act of discovery. Our gaze crossing theirs, separated by time, joined by light. If such an intelligence exists, they too live under a sky full of mysteries. They too face the same limits: physics, distance, the slowness of light. Perhaps, like us, they've realized that reaching another star may never happen in their lifetime. But still, they look, because maybe that's what awareness means in this universe, not just to exist, but to seek. To ask questions in the dark, trusting that somewhere, someone else might be asking them too. If they are out there, watching our sun rise faintly in their alien sky, then we are already connected, not by proximity, but by wonder. Two civilizations separated by 4 years of light, both alive, both reaching, both whispering into the void the same eternal question: is anyone else awake? The space between stars may be the universe's way of teaching humility. We are small, but not insignificant. Each question we ask reaches a little farther into forever. For all its vastness, the universe is not cruel. It does not keep its secrets out of malice, but out of necessity. Distance is how it maintains its rhythm, how it allows time for stars to live and die, for planets to form, for life to rise and wonder at its own existence. The space between the stars is not a void, it's the silence between heartbeats, the pause that gives meaning to sound. Without it, there would be no harmony, only chaos. When we first measured the distance to Alpha Centauri, it felt like an unimaginable gulf. 4 light-years, a number so large it almost mocked us. Yet that distance is what makes the dream possible. If the stars were close together, if their gravity and heat intertwined, there would be no stable worlds, no calm skies, no long, quiet epochs for life to learn itself. The vastness we struggle against is the very condition that allows us to exist. In that sense, the universe's distance is not rejection, it's protection. Every question we ask, every observation we make, is an act of reaching across that separation. When we study the faint flicker of a distant sun, when we send probes into the dark, when we listen for the faintest whisper from another world, we are participating in a cosmic conversation older than language. Each photon of starlight that touches our eyes has traveled across eternity to meet us, and by seeing it, by understanding it, we complete its journey. Distance humbles us, yes, but it also ennobles us, because to be aware of how far the stars are is to understand the miracle of consciousness itself, that something small, fragile, and fleeting can comprehend the infinite, that we, bound to one tiny world, can look up and trace the shape of galaxies, can measure time in the shimmer of ancient light, can imagine futures far beyond our reach. Perhaps that's the true purpose of distance, not to keep us apart from the stars, but to give us something vast enough to grow into, to remind us that meaning is not found in arrival, but in the act of striving. Every discovery we make, every dream we pass on, extends the reach of awareness itself. We are, in the grandest sense, the universe becoming conscious of its own expanse. The distance between stars is not emptiness, it is thought made space, potential made real. When we ask how far, the universe answers not with discouragement, but with invitation. And maybe that's what Alpha Centauri truly represents, not the next destination, but the next question, a reminder that we are meant to wonder, that the journey is not to the stars, but into the infinite depths of understanding itself. For as long as we keep asking, as long as we keep looking outward, the space between us and forever will keep shrinking. One question, one photon, one heartbeat at a time. As we drift back from the map of impossibilities we traced tonight, let your mind soften around what we learned. Alpha Centauri remains both astonishingly near and impossibly distant. 4 light-years of empty, patient space that turns speed into centuries, fuel into dreams, and the bravest engineering into careful thought experiments. We met the tyranny of distance, the stubborn limits of chemical rockets, the impossible energy bills of near-light travel, the silent danger of dust and radiation, and the quiet loneliness of messages that take years to return. We held up fragile solutions, sails bathed in laser light, fusion engines that live only in equations, tiny robotic emissaries racing on fragile foils, and we watched how each answer reshaped the question rather than erased it. None of this is a final failure. It is a catalogue of constraints, a cartography of what the cosmos asks of us. The lessons are gifts, humility about scale, curiosity about physics, and creativity in the face of limits. We found consolation in what we can do now. To send tiny probes, to sharpen telescopes, to learn the chemistry of far worlds with patient instruments that read starlight like a letter. We discovered that the act of wondering itself stretches humanity, turning impossibility into purpose. So tonight, be grateful for the smallness and the splendor both. Be grateful that you exist on a planet surrounded by protective light and familiar gravity. Grateful that, even from here, we can taste the stories of other suns. Let the quiet vastness of the void remind you that rest is part of the journey. Purpose need not always be movement. If this voyage through thought moved you, a like or a gentle subscribe helps keep these small, slow explorations alive. Now allow your breath to lengthen, your heartbeat to slow, and your thoughts to glide like photons across the night. Imagine the stars as soft, patient lights watching over you. Sleep now, safe in the small warmth of home. dreaming of distant suns. Good night.